Radha, you can start.
Good morning, everyone. So to say it's a great pleasure to be a part of this conference, and I'm sure all of you are taking great in participating in the same. And it is my pleasure to introduce Professor Sai Vinyanpatti. He has done his master's from IIT Madras and PhD from Louisiana State University in 2010, and then did postdoctoral studies at Massachusetts, Boston. He joined the Center for Quantum Technologies at National University, Singapore. He's still a visiting fellow there. And 2016, he joined IIT Bombay, and he's leading the Quantum Information and Technology Group. His interests are in quantum information theory, quantum control theory, quantum thermodynamics, and quantum synchronization. So today's talk, I'm sure, is a area of interest for all of us, whether you're in with talking of theoretical or experimental, because finally we all rely on the information technology today. So with this, I will pass on to Professor Sai, and let us hear from him what he has to say today. Thank you very much.
Thank you, Professor Radha Srinivasan, and also thank you, Professor Mishra, for the kind invitation. I'm very, very honored, and I'm very happy to be here today. This is, I think, something that doesn't quite happen often, and so I'm excited to be, at the epoch of a new center. Such centers, as all of you know, in India have often been kind of places of excellence. They've congealed the best talent that exists in the country around it, and so I expect exactly the same with our new center here with Bombay University, and so I expect that in the coming days we'll see a lot of great work coming from them. And so I'm very happy to be here to kind of deliver one of the inaugural lectures for it. So let me just, so you can see the title slide?
Yes.
Okay, perfect. So let me take it away with that. So today I'm here to talk to you about, for the next hour, I'm here to talk to you about something that's a very simple question, but that has an aspect of theoretical physics, an aspect of computational physics, and has an aspect also of applications. So it's a simple question, which is, how does a quantum system evolve? So, sorry, can you also see my cursor moving?
Yes, you can.
Okay, perfect. And so this question basically has applications in simple things like nuclear decay. So this is perhaps one of the first places that this kind of question came up. But also it has applications in things like three-level lasers, spontaneous and stimulated emission. It has applications in modern ideas about synchronization and lasing in few-level systems. It has applications in basically things such as quantum machine learning, which is kind of a very modern up-and-coming field, and also quantum control theory, which is another field that is of interest for me. So with that, let me just quickly walk you through the outline of the talk. So what I'll talk to you about today is just for pedagogical reasons, just so that the students who are new here can also follow along the discussion. I'll start with a brief discussion on what is an open quantum system, and then basically I'll talk about the challenges in simulating open quantum systems. And then I'll walk you through a bunch of exact solutions and well-known results. And I'll basically briefly detour over to Markovian master equations, where basically Professor Sudarshan, of course, in the great theoretical tradition of our country, has kind of some important contributions. And then I'll talk about a general solution, which is written in terms of the so-called Liouville superoperators. And then I'll briefly mention some computational aspects without kind of going into any detail. And then beyond Liouville superoperator theory, there are many directions to take, one of which is non-Markovian evolution, which I won't talk about, but I just put it here because it's another interest of mine. I'm happy to talk about it offline. And I'll talk about NISC algorithms a little bit and conclude with basically a modern approach to kind of quantum machine learning. So it's a lot that I've taken on my plate, so hopefully I can deliver. What I want to emphasize is basically that you can, roughly speaking, split this into 3 boxes. The talk. The first box is basically purely theoretical. It's the foundational questions about open quantum systems theory. It's the foundational questions about the universe we live in. It's the foundational questions about the interiors versus the exteriors of black holes, so on and so forth. The second is basically a computational aspect, has a large computational aspect to it. So if you're interested in real physical systems, if you're interested in condensed matter systems, so on and so forth, then you can't stop here. You have to also contend with some of the stuff that's here. And then I want to kind of proceed towards modern quantum computing theory and its intersection with all of this stuff by kind of highlighting the connections and also the way that we get pulled into it. And so I think this is exciting for that reason. I also want to, in the spirit of the workshop, basically point out that a lot of these which I've highlighted here are still outstanding challenges in the field. So, so what is the, the challenges in simulating open quantum systems is a whole field, so on and so forth. So each of these is actually kind of an active area of interest with several researchers in it. So I want to emphasize that as well. Okay, so with that, let me just get going. So let us start where we know on solid ground, which is basically I know how to write down the Schrodinger equation for a single particle. So if I have a single quantum system, the cartoon of it is this thing right here. Then of course I can write Schrodinger's equation for it. I psi dot is H psi, and then with some initial condition psi naught. And so I can solve it in terms of its coefficients. So if I take 2 coefficients C0 and C1, then I can write psi of t in general as C0 ket 0 and C1 ket 1. And this ket 0 and ket 1 are just 2 fixed vectors in the vector space. And then what I can do is I can write this equation out. It will just be a vector, a matrix equation. And then I expand out, and then I can solve the couple time-dependent differential equations. What happens if I couple another quantum system to it? So let's say I bring an identical atom and I start talking to it. Then the story becomes a little bit more interesting. And here I have to consider now 4 terms, not, I had 2, now I'm going to 4. And the 4 terms is basically C00, 01, 10, and 11. Right? Those are the 4 quantum states available. Now, likewise, if I go to basically n quantum systems which are interacting with each other, you can already see that there is an exponential number of terms because I went from 2 to 2 square here. So if I had 3 particles, I'd go to 2 cubed, so on and so forth. And so in general, my quantum state I could write in some decomposition as k going from 0 to 2 to the n minus 1 times ck times k. And this is just the digital representation of this quantum state. And so there are 2 to the n minus 1 numbers that I have to keep track of, basically. And so this is one way of perhaps beginning to understand that this is a difficult problem in general. Now, let me just say that that there is some attention that you have to pay a little bit. So n coins, basically, which you flip, also have 2 to the n possibilities. So 2 to the n per se is not enough to basically sufficiently justify that this is a difficult problem. And the way of the difficulty is basically something that, the technical definition of what it means to be difficult is something that is a talk onto itself. So I make some questions. I pose some questions here, and the answers to which will be interesting. I also want to highlight that solving in general the problem of these kinds of interacting quantum systems is the kind of thing that people do in materials research often, and all of the kind of theories there, density function theory, so on and so forth, are custom built to kind of solve these kinds of problems with certain caveats and assumptions loaded there. So from that perspective, I point you to tomorrow's talk by Professor Shobhana Narasimhan that I saw in the schedule. Okay, so with that, let me just tell you the perspective that I want to take, or just a little piece of information that I want to carry with me going forward. And that little piece of information is that the thing that quantum computing as a field pays attention to is entanglement. And entanglement can be simply stated this way, which is that if my quantum systems, I have n of them now. So remember that I had this cartoon to the tensor product n. So if I have n of them now, which I just label somehow, if each of them can be written as a quantum state onto itself with no relationship to anything else, then the mathematical structure that I would write is basically a tensor product of these n quantum systems. And in that case, this is actually an easy problem to solve because you just solve each of them separately and put them together. The difficult problem is basically where you have this kind of a situation where UA, UB, UC, so on and so forth are eigenvectors corresponding to the space A, B, C. They don't have to be the same eigenvectors. I've just labeled them likewise for convenience. And then they appear with some coefficients lambda, it's called a Schmidt decomposition. And so when you have these kinds of quantum systems, then basically you with large number of terms, then this becomes kind of difficult to simulate. You can make an argument that this is difficult to simulate. So this is a point that I will return to later. I just want to kind of just pepper it in here, basically just to give you an indication that already the question of whether or not a quantum system is easy to simulate or difficult to simulate, which is a computational question, is already in the middle of the discussion now. So we're right in the middle of it already. Okay. So there is a different problem that I want to take on, which is the open systems problem. And so the way I state that question is thusly. So again, I focus on one cartoon, the cartoon of one quantum system. So here it is. I've just put it in the middle. But when I solve Schrodinger's equation, what do I say? I basically say that there are no interactions. This is not interacting with anything else, right? But in real life, this is not true. In real life, what is true is that this thing is actually part of an environment of similar systems, dissimilar systems with which it's interacting. The simplest example I can give you is think of a simple pendulum, which is swinging from a suspension. The simple pendulum is, of course, interacting with the air in the room that you're performing the experiment. But when you write, 2 pi square root L over G, you just ignore the air, you ignore friction. And so the isolated system assumption that we often use to write down problems and solutions in classical mechanics is a convenience, and it's a convenient first approach to the problem, but it's not the complete problem. And in fact, as we well know in the damped harmonic oscillator case, this incompleteness of the solution means that we get a lot of the details wrong, and we need to go back and fix that by putting in a damping. So the damping here is basically represented by basically the fact that there are a bunch of environmental atoms that this atom is interacting with. The thing that I emphasize is that we're not interested in the environmental quantum system. So I don't care what's happening to this white atom here. I'm only interested in what's happening to the central red atom. Even though these white atoms can talk to each other and they talk to the red atom, with some kind of prescribed Hamiltonian. So if you have an Ising Hamiltonian or whatever, that's the way in which these things talk to each other. So how do I solve this problem now? And the way I can solve this problem is basically I can say, look, for the isolated quantum system, I know what the Schrodinger equation is. When I made the assumption in my head that this and this alone was the only atom, my hydrogen atom was the only atom in the universe, I could very easily write the Schrodinger equation for it down. That's the fundamental equation. I said dot is H psi. But now you're telling me that that's not the only atom. You're actually telling me that there is a collection of atoms, right? Like I just showed you in the cartoon before. Well, I could take the following point of view. I could say, well, I just draw a box around it. That's the box that I've drawn already. And that box is now an isolated quantum system. There is nothing outside of it because I've taken into account all of the system and all of the environment around it. And once I've taken into account all of the system plus the environment around it, I can again write the Schrodinger equation for the whole system plus environment. So remember here that this system S corresponds to this red quantum system in this cartoon, and the E corresponds to all of the white quantum systems that I've represented in this cartoon, right? So I psi dot is H psi is again true, but it's true now at a much different level. It's true for the tensor product space that consists of one system and n minus one environmental degrees of freedom. So I can write this down and I can solve it. And this is one way to think about approaching open quantum systems as a whole. This already, the fact that for the isolated system, I have a Schrodinger equation, but for the full system also, I have a Schrodinger equation, automatically means that I actually have, I already have conceded away something about the system alone. And this is what I want to show you. What this implies for the system alone is the following, which is suppose I'm interested in only an expectation value of the system, right? After all, I'm only interested in the system. I'm not interested in the environment. So I take the operator expectation value of some operator A, and you can write it down. It's basically A times basically UQ, VQ, VK, right? And what I've done is I've written psi as a expansion of CK times UK tensor VK, and then this appears with a different dummy index Q, and that's why I get this equation. But if I just assume for a moment, I'm making some mathematical conveniences which I'm not explaining, but if I assume for a moment that this is just orthonormal states, this is just the Dirac delta function, the Kronecker delta function. And so I can get rid of one of these indices. I can get rid of the Q, the K, and then I can write everything in terms of Q. And what I get is mod CQ squared. So because K becomes Q, CQ star CQ is just mod CQ squared. UQ, both the bra and the ket become UQ. And that expectation value I can write conveniently as simply the trace of another object rho times A. And what is rho? Rho is simply basically mod CQ square, which are now called PQ, times the outer product of UQ, right? So all I want you to take away from this is that the existence of this second subsystem, whose eigenvectors are V, VK, implies that the system state alone is not given by a pure state. It's not given by a wave function. Instead, it is given by a more complicated object called a density matrix. And this density matrix rho, which I can write with the superscript S to indicate that it's a system, but I'll just drop it and just call it rho. This density matrix rho is simply given by a convex mixture, which means a probabilistic combination, a convex mixture of the outer products of pure states, basically. And so that's the technical definition of what a density matrix is. And it simulates basically, or it is the representative of all open quantum system evolution. So the moment I basically have, I have this kind of a system where I have a system interacting with a bunch of environmental degrees of freedom, and I want to write down what is the description of this system, the state of the system. The state of the system is no longer a wave function, but it is in fact a density matrix rho. So for the rest of this talk, I'll basically only focus myself on the density matrix, its properties, its evolution, its simulation, so on and so forth. And so this I just wanted to carry with you, that I have an interacting quantum system, a system that's interacting with an environment. I don't care about the environment. Immediately, this means that the quantum state that describes the system alone is in fact given by a density matrix. It's given by a matrix and not a wave function, right? This is what I want you to take away. Okay, so with this, I can ask the following question. I can say, okay, I have now written down rho as basically some PQ times UQ. So I've made some abstract statement about what my quantum state of an open quantum system is. What are the properties of this object, right? So, well, if I give you an n by n matrix, can I tell whether this is a density matrix or not? Because if I can't even tell this is a density matrix, I'm in trouble. Well, thankfully we can. There's some very simple properties that you just have to follow. The first of these is basically that rho is evidently Hermitian. You can just check, because this is a Hermitian construction. It's the outer product of a vector with itself, and this is basically a real number PQ. This object is entirely self-adjoint. You can just check this by by inspection. The second thing that I want you to notice is positivity. All the eigenvalues of rho are given by PQ, and PQ is evidently positive because they're mod CQ squared. They're the absolute value squared of a complex number, and what that basically means is that this number is real and positive semi-definite. And so this basically is the same thing as saying that the eigenvalues of rho are positive semi-definite, which is often indicated by simply rho greater than 0. Matrix greater than 0 basically means its eigenvalues are greater than 0. And the third is basically the condition that the trace has to be 1. This is a probability theory. PQ is a probability distribution, which means that it has to sum to 1. So these two have to do with the fact that PQ has sum to 1, and hermiticity has to do with the fact that PQ is real, and these are basically the self-adjoint operators. And so the three of these conditions, if they're satisfied, you have a valid density matrix. Any valid density matrix should have these three conditions satisfied. So that if then only if conditions, basically. So I can basically now ask the following question. I have described a very generic density matrix. A generic density matrix is some n by n matrix that you produce in front of me, whose entries are filled out with some numbers, such that basically it can be decomposed as this sum. Okay, I agree with this for the moment. Now I can ask the question: how does a generic density matrix rho? What is the mathematical transformation that describes a generic evolution? Right. This must say for a generic density matrix rho. What is the mathematical transformation that describes the generic evolution? Right? Is the program clear? It's exactly the same way that we would go about any other problem in physics, which is I have a particle that's basically colliding with other particles and traveling in water. And now I ask questions like, what's the most general theory that I can write down for the particle? What's the most general description that I need for the particle? Do I describe it as a point in phase space? Do I describe it as a probability distribution? And once I've described it, what's the evolution equation for whatever it is that's the state description? So the first thing we did was we described the state. Just like in Schrodinger's equation, in quantum mechanics, the state is given by a wave function. Here, for open quantum systems, the state is given by a density matrix. Now we're asking the question, now that I give you a density matrix, if it evolves in time, what does it look like? Right? Okay. So I state basically two things without any proof, because this would take too long. It's a lecture onto itself. But both of these are basically seminal contributions by George Sudarshan to the field, and so I urge you to look them up. The first of these is basically a discrete time approach, basically. So where what you do is you take rho at some time t0, and you basically say, I want to take rho at time t0 to another rho prime at time t prime. So which basically means I look at my density matrix at time at the initial time, and I look at my density matrix at the final time. What's the matrix that connects these two? Because these two are matrices now. What's the matrix that connects these two? Right, and so a complete characterization of this matrix, which connects these two, and basically a restatement of that matrix, a transformation of that matrix with some very nice block positivity properties and so on and so forth, is actually the essence of the discrete time paper. It's a very famous paper. It's called MSR, and so the SMR paper. So Sudarshan, Matthews, and Rao. Is this one, and I will say no more about this. I just wanted to put it here just to highlight that this paper exists for those of you who are new to the field. Another kind of more careful, a different direction, but that has kind of far more immediate applications, is basically to ask, what's the differential equation for rho? Right? After all, what is rho? Rho is just a quantum system that's evolving in time, which means that just like Schrodinger equation is a differential equation, I could expect that there is a continuous time evolution, because after all, closed systems are examples of open systems. There's just no environment. So, so I can ask, what's the differential equation for basically this new object rho that you've just invented, 10 minutes ago? And the answer is basically, I again state this without any proof, but I make some remarks about it. The answer is an equation like this. So it's rho dot is minus I h rho. This is just Schrodinger equation. This first part is just Schrodinger equation. So this is typically called the Liebel-von Neumann equation. And then the second part is basically this new piece of physics that comes. And these are written in terms of numbers gamma k. So they're rates, they're called rates gamma k. So in terms of dimensionality, they're inverse time. The frequency, they have dimensionality of frequency. And operators xk. So operators x now act from the left and the right, basically, onto the density matrix, and that full equation is the general equation, right? Now I have not explained how I got this equation, so let me justify the equation. So I'm not explaining to you how I got it. Now that I have it, I'm justifying it to you, which is a different, which is a weaker thing, but it suffices, I think, for the talk. So the first is basically, what do I know about density matrices rho? They have to be Hermitian. So if I write rho of t as rho of t plus delta t as rho of t plus d rho by dt times delta t, so just essentially just a first order expansion, then d rho by dt is this object. This is the differential equation. So rho, if this rho I am evaluating at a slightly future time t plus delta t, then for rho, for the density matrix to be Hermitian, this equation has to be Hermitian, because it's rho of t plus d rho by dt times delta t. So d rho by dt basically has to carry the same, carry all of the same properties. So d rho by dt has to be Hermitian as well, and you can check that this is a Hermitian object. X rho x dagger is self-adjoint. If you have ABC transpose is C transpose B transpose A transpose, So when you do that in the reverse order, you basically get back x row x dagger. You can just check this. Likewise, this object is basically just transforms to itself as well. So this whole thing actually is a Hermitian construction. And so it preserves hermiticity. So the density matrix preserves hermiticity. The second is positivity, which is basically a slightly technical thing. And it has to do with basically whether gamma k is positive or not. And so let me just say that gamma k has to be positive always. And then basically positivity is ensured. So this places a condition on gamma k. Gamma k can't be anything it wants to be. And the third is trace preserving. So if I take, again, I go back to the equation, rho of t plus dt is rho of t plus d rho by dt times dt. If I take trace on both sides, trace of rho of t plus delta t, density matrix at a future time, is 1. Trace of the density matrix now is 1, which means the trace of d rho by dt has to be 0. Trace can't change. That's what it means. So because trace is constant, d rho by dt's trace has to be 0. And this you can check as a traceless operation. In this big bracket, the trace, if you just compute and use cyclic property of trace, it goes to 0 identically. And so that entire thing just goes to 0, and which means that it preserves all of these 3 properties. This if you put a condition on gamma k, basically. And that's the way in which you can think of this open quantum system equation. Yeah. So with that, let me just go forward. Sorry, if there are any questions, you can of course just pause and interrupt me and ask me. I think if you raise your hands, I can just request if the moderators can just ping it at me, because I can't see the Zoom screen as well. So with that, let me just take this and continue for the rest of the talk. Let me ask the following question, which is, how do I find the solution to an equation that this equation? So if I give you this equation, or how do I find its solution? And the solution, it turns out, is actually, there are many things that people have worked out. This is a very old equation. And so I want to show you basically one aspect of each of these. So the first of these is basically exactly solvable models, and I actually want to spend a little bit of time trying to show you the solutions. Then I'll also show you, I'll make a comment on approximate solutions. That's a whole other talk, which I'm very excited by. I'm happy to talk to you about it offline. Then there is basically numerical integration as kind of a last resort, a last ditch method if the exact and approximate solutions are either insufficient or don't work. And then there is basically the really last resort option, which is quantum simulations. And what I will do is I will approach each of these, and by the time we get to quantum simulations, we'll be in quantum computing. Basically, we'll be in the area of quantum technologies where we're trying to simulate quantum systems. Okay. So let me tell you about exact solutions first. So, well, of course, the first and simplest example is I switch off xk. I just turn off the Lindblad term. So let me just remind you again. Xk is this stuff. So if I turn this off, then I'm just left with rho dot is minus I h rho, which is a Schrodinger equation, right? It's just the same as I psi dot is h psi, right? And so if xk is 0, then basically rho dot is minus I h rho. You can just see, to see that this is a solution. All you have to do is just say if rho naught is actually an eigenstate E lambda of the quantum system, then the Hamiltonian commutes with its own eigenvectors. And what that means is that rho of p is basically just the same E lambda, which means that this rho of p is unevolving. So a solution is automatically available if xk are 0, then just diagonalize hk, and the eigenvectors of hk are basically solutions. And you can basically then write a general solution in terms of the eigenvectors as well. So this is what we do in time-independent and time-dependent Schrodinger equation, right? So this little solution in this box, if I just put a box around it, is the first course on quantum mechanics, right? It's the very first course that we take. Now, what happens if xk is not equal to 0? I bring you good news. So at least one steady state is guaranteed. And this basically is a very important statement in open quantum systems theory. So let me show you this by actually showing you several solutions and then telling you what the word steady state means in this case, right? So let me show you the solutions, the exact solutions to this problem, or families of solutions. So the first solution example that I want to show you is actually just direct integration. You just write the differential equations down and just solve them. There is nothing more to it. And so this is basically, I show you by the way of what's called the phase damping map. And so the phase damping map is a very famous map in quantum computing. What it represents is basically I have a quantum state along the Bloch sphere, somewhere on the Bloch sphere. So this is the poly sigma x eigenvector plus one eigenvector, the poly sigma y and the poly sigma z plus one eigenvector. So they form kind of this directions on the Bloch sphere. So what the phase damping map does is it preserves the z direction, but it actually decays the quantum state along the x and the y direction. I'll show you that this is true, but this is what it does physically. So what it does is it preserves the population information, but it kills the coherence between 0 and 1. This is physically what it does, right? And so how do you see this in an evolution equation? So rho dot is gamma over 2 z rho z minus rho. So right rho is basically a block vector. So the way you write it as a block vector is 1 plus r dot sigma divided by 2. So remember that this is absolutely true. I mean, even if you've never seen this before, this is true, because any quantum system, any 2 by 2 matrix can be written in terms of the poly basis, identity, and the 3 poly matrices. And now trace is preserved, which means that the trace is always 1. So if you take the trace of this, poly are traceless, and then identity over 2 has trace 1. So this is very general density matrix. I've said nothing about what the density matrix is by making this comment. So now if I take a rho dot and then I plug in basically this gamma over 2 z rho z minus rho. So this r prime is this z rho z, whatever is happening to the r density matrix because of z rho z. I've just rewritten it as r prime minus r times rho, right? And so all I need to do is just work out what this r prime is by simply working out what z acting on r dot sigma acting on z is, right? R dot sigma is a matrix, so I have to now perform this matrix multiplication. If I do that, I just show you the solution. If I do that, then what I get is r dot of x comma y is minus gamma times r of x comma y, which basically means that if I integrate it up, I immediately get the solution r of x comma y as a function of time is e to the minus gamma t times r of x comma y at the initial time t, right? At the initial time t equals 0. And r dot of z is given by 0. It's just flat 0, which means that z is preserved in time. So the general density matrix, which I can write as 1 plus rz, 1 minus rz along the diagonals, rx minus iry and rx plus iry. This is just the poly decomposition that I just showed you a second ago, just written out as a matrix, as a 2 by 2 matrix. The steady state is basically this density matrix rho at time t equals infinity. So I'm just taking infinite amount of time and asking what happens to the density matrix. Remember that that these solutions are open quantum system solutions, which means they're solutions where the quantum system can decay into the ground state. There can be nuclear decay down into a state where they don't change at all. They could also just be looping around like Hamiltonian dynamics. These are the two solutions that are available. In general, if you have dissipative systems, in general, you will have these kinds of steady states which settle down, basically. Not necessarily, but I'll get to that in a second. So, so rho at infinity is basically 1 plus rz and 1 minus rz along the diagonals. This is exactly what I just said a second ago, which is that the solution preserves the z, the population information, but it completely kills the coherence information. So if you started the density matrix off with some initial coherence r, x, y, comma, z at 0, it's completely gone. At asymptotically at infinite time, all you can see is basically that 37% of it was in the excited state and the rest of it was in the ground state. That's it. That's the only information that's available to you. I also want you to notice that there are multiple steady states here, which means that for every value of rz, this is actually a new steady state that's available. Any value of rz is preserved in this solution. And this is also something that we will come to in a second. This is also an important complication for open quantum system evolution. Okay, so the second solution I want to show you 4 solutions. The second solution I want to show you is by Baumgartner and Thirring. It's a very famous solution. It's earlier than the third solution I'm going to show you, but it's later than the third solution I'm going to show you, but I think this way makes pedagogical sense. So Baumgartner and Thirring basically proposed the following solution. They said, okay, what do you want to solve? You want to solve Schrodinger, Lindblad equation, this general equation. So what we do is basically, let's just write this rho dot without the Hamiltonian part, right? So remember, just to recap, this has this Hamiltonian part, and then this part is typically called the Lindblad part, and these operators are called the Lindblad operators. It's after the authors who basically worked on this, and the equation as a whole is typically called the GLKS equation. I wanted to mention it and I forgot. I'm sorry. Right? And so to go back to this solution that I was saying, Baumgartner thing basically said, if you have rho dot is basically purely Lindbladian, so there's no Hamiltonian part, then let's just make the following two assertions. Assertion number one, if x acting on some vector 0, I just call it 0, anticipating that it's the steady state of my system. If x acting on 0 is 0, then rho infinity is 0, right? It's just the outer product of 0 with 0. And the proof of this is trivial. Just check by substituting basically. Rho dot is x rho x dagger. So, just say rho is this at time t. What happens at time t plus delta t? And then x acting on 0 is 0, which means the whole thing switches off. The whole thing goes to 0, which means rho dot is 0, which means 0, 0 is preserved in the evolution. That's it. That's the whole proof. On the other hand, they said if there is no such ket exists, then the following ket is actually the following density matrix is actually the steady state density matrix. And again, the proof of this is just substitution. So you can substitute and you can check that x dagger x to the -1 divided by trace of x dagger x to the -1, in fact, is an invariant of the motion. So if you substitute it into rho dot, that whole thing, then the whole thing just goes to 0. Okay. Now, let's actually work that solution out for the phase damping map. So for the phase damping map, what I have is rho infinity. Again, this is Baumgartner's solution. Is this x dagger x to the -1 divided by trace of x dagger x to the -1. And now if I basically ask what is it for a phase damping map, right? This example that I just gave you a second ago. For a phase damping map, x is basically sigma z, right? It's just the poly sigma z, which means that x dagger x is the identity matrix. And because it's the identity matrix, what this implies is that the Baumgartner-Thirring solution, you can check, is simply identity matrix divided by trace of identity matrix, which is identity divided by 2, right? So one thing I want you to notice is that Baumgartner-Thirring solution is missing the mixture. It's saying there's only one solution, and that solution is the identity matrix. But actually, we know that any combination of populations is actually, it doesn't have to be 50-50. It can be 20-80, it can be 30-70, anything will work, basically. And so this mixture is basically missing from the Baumgartner-Thirring solution. But again, this was one of the important solutions that proved that if everything else is, if all other hope was lost, there is at least one steady state. And this one steady state was an important outstanding problem basically for the field. Okay. So now I show you another solution by Puri and Lavande. So this is from 1979, so many years before Baumgartner-Thirring. And so this solution basically is quite interesting. So what they did was they basically said, well, let's take this this form which I showed you in the Baumgartner-Thirring, and let's add a Hamiltonian, which is basically x plus x dagger. The same x that appears in the Lindblad appears here as well. Why is this important? Because for Puri and Lavande, x was actually s minus the annihilation operator basically for spins. So the poly sigma minus for a single 2-level atom, for instance. So what this means was sigma minus plus sigma plus is just sigma x, is proportional to sigma x. And so the coherent term is just poly sigma x, which makes perfect sense. It's just driving along, transverse driving basically. And so this makes perfect sense that this is a problem that would come up in kind of standard quantum optics, where basically you just have damping towards the ground state, but you have coherent driving along in the Hamiltonian direction. What they basically proposed was they said, well, take s plus minus, this operator s plus minus, the lowering and raising operator, and promote it to a complex operator, which is basically a different operator, which is basically s plus minus tilde, which is s plus minus or plus a constant, and this constant has the ratio of the coherent driving to the decoherence rates. So this ratio is, so this is the identity matrix coming here. So this, what they showed, you can just check this by substitution. What they showed was that if you write it in this fashion, then the Baumgartner, so then this evolution simply looks like the Baumgartner-Thirring evolution with the new lowering operators and raising operators. So this Hamiltonian gets absorbed into the Lindbladian part, right? This is all it means. So in the modern language, what I would say is that this Hamiltonian part emerged as the Hermitian part of the Lindbladian, and so you can pull it out and write it this way, but you can just as easily absorb it back in. No problem. And so now if you look at the solution, and in the rho infinity is this complicated object, which is s plus s minus tilde inverse. And this tilde basically means that you get the product of two terms which basically have, you know, complicated. So this density matrix is not simple, is all I want to say. And the important thing that I want to point out was that, you know, since 1979 and for many dozens of papers since then, this important solution has had huge implications to quantum optics, to resonance fluorescence, and so on and so forth. So it has huge applications in many fields of quantum optics that we know and love. Okay. So that was all of the kind of differential equations type solutions that have existed. Now I want to focus my attention to a much more general kind of class of solutions, which is this Liouville space solutions. So let me begin by basically saying that the Lindblad equation GKLS is basically still linear in the density matrix. So look at this equation. Rho dot appears once on the left-hand side. On the right-hand side, rho appears once in this equation and once in this equation, right? Rho appears linearly here and linearly here. So every term on the right-hand side is linear in the density matrix. So if I write out element by element, the density matrix evolution is just a linear equation. There's nothing else to it. So that's all the Liouville superoperator theory is. So what it says is, it says you can stack the density matrix according to its columns, for instance. Rho 1, 1, rho 2, 1 go first, and then rho 1, 2, rho 2, 2 go next. So this is just a stacking of the columns of the density matrix. And then if you write this Lindblad equation out, then it looks essentially like rho dot is L acting on rho. This vector rho is basically just this column vector. It's the vectorized density matrix. And L is now something called a Liouville superoperator. You can see that there are these two hats on it, because it's not an operator that acts on states. It's an operator that acts on other operators. It acts on density matrices. And so this is called a superoperator. And so this Liouville superoperator theory is essentially one of the modern pillars of open quantum systems theory. And so how does it look? So here is an example that I've just worked out for you. So suppose I want to basically take two quantum states, psi j and phi j, which have different eigenvalues ej and ek, for a quantum system which just has a Hamiltonian, which just has a unity. Then what I can do is I can ask, how do quantum states transform? I just told you that I take the quantum states, the 2 by 2 matrix, and I vectorize it and I put it as a column matrix. How do quantum operators transform? Because not only do I have to tell you how states transform when I do quantum mechanics, I have to tell you how operators transform, because we are only interested in expectation values. Operators transform according to this law. B rho C goes to C star rho B, C star tensor B acting on rho. This is a kind of complicated looking object, but you know, it makes perfect sense. And as an example, I urge you to work this out at home. As an example, you can take basically two eigenvectors, psi j with eigenvalue ej and phi k with eigenvalue ek, and you can write this column vector times this row vector. So this is the column vector corresponding to basically psi and phi, and the row vector corresponding to psi and phi, and you can write out the density matrix for it. And then you can write, this is not quite a density matrix, but ignore that for the moment, this outer product. And then what you can write down is, you can write down basically the columnized vector for it. And you can show that this unity, which is U transpose tensor U, which is exactly this object. Remember that U dagger basically is conjugate transpose, which means that if you do two conjugates, you are left just with the transpose, and that's the reason why you have a transpose here. U transpose tensor U is just an eigenoperator with eigenvalue, which has the correct eigenvalue. So you can start with two eigenstates with energy E1 and E2 and end up with exactly the difference of energies when you compute basically this particular U acting on this particular state, which simply is a verification to convince you that the C star tensor product B is actually a good way to represent rho. Okay. But let me just show you a concrete example, because this is maybe a little bit abstract. It's getting a little bit abstract. I go back to the exact same problem again. I go back to basically the question of my Liouville superoperator for the phase damping map. And the Liouville superoperator for the phase damping map is basically given by gamma over 2 sigma z tensor sigma z minus identity. I've used the same rules as before. So what I've done is, remember that my phase damping map was rho sigma z minus rho, which means it's sigma z was acting twice from left and right. Identity active was acting twice, and the difference of the two was the operator. So if I just do the Liouville superoperator for it, it's z acting twice, identity acting twice, and the difference is this Liouville superoperator with the correct coefficient. And if you just evaluate this matrix, you can check that this matrix is simply minus gamma 0 0. So if I start with 1 0 0 0, right, this state, that's a steady state because it doesn't care. It's a 0 of the Liouville superoperator. If I start with 0 0 0 1, so if I start in the outer wings where there is a 0 here, I just get a steady state immediately. In fact, any convex mixture of these two is also a steady state. So the mixture solution that we first found by direct integration is available to us again by the Liouville superoperator theory, whereas the Baumgartner solution seemed to have missed it, right? Okay, so this is one thing that I want you to notice. Another thing I want you to notice is that this thing is order n to the 4. So this density matrix was a 2 by 2 matrix, which means that it simply had 4 elements in it. But the Liouville superoperator has to take a density matrix to a density matrix. So it has to take a 4-dimensional vector to a 4-dimensional vector, which means it's a 4 by 4 matrix. And a 4 by 4 matrix has order 16 numbers in it. So that is the n to the 4. It's 2 to the power of 4. So this n to the power of 4, I just want you to notice here. So a 2 by 1 vector for quantum states became a 2 by 2 for the density matrix. A 2 by 2 became a 4 by 4 for the Liouville superoperator. This growth is actually exponential, and this exponential growth is something that I want you to notice because I'll come back to it. Okay, so with this, let me just say what is the general way to solve these kinds of problems. The general way is basically you write down the density matrix evolution equation, the GLKS equation. Then what you do is you convert it to Liouville space. So this way you basically go from, you can vectorize the density matrix. Then a simple solution the moment you convert it to Liouville space is simply given by e to the LT acting on rho 0. That's it. For time independent Hamiltonians and Liouvilleans, this is Lindbladians, this is true. Then what you do is you look at the transients and asymptotics by looking at the eigenspectrum of L, because e to the LT acting on rho 0 basically has the same form as e to the MT acting on a vector V. So the eigenvectors of M basically become the important quantities, right? The only thing I just want to emphasize is that L is not equal to L dagger. It's not a self-adjoint matrix, which causes some issues downstream, which I'll point out in a second. Okay, just to kind of set up, the rest of this conversation, but also Professor Sudeshna's lecture, which is coming next. Recap from standard classical mechanics. I just want you to recap that if I have a matrix M, which is some ABCD, its trace is basically the sum of the eigenvalues, and its determinant is the product of the eigenvalues. And its eigenvalues themselves are written as a linear combination of the trace and the determinant, right? There are only so many invariants of the matrix. And so when I take M, and if it is invertible, then I can simply diagonalize it. I can do SDS inverse. And any vector which basically has the equation V dot is MV. This is exactly the same as rho dot is L rho. It's the same Liouville equation form. V dot is MV basically has only, you can very quickly solve it by basically pre-multiplying, post-multiplying by S. So you can write M as DS inverse times V, and you can pre-multiply by S inverse, which means S inverse V dot is D S inverse V. So I can write it as X dot is DX, where D is basically just the diagonal containing the two eigenvalues lambda 1 and lambda 2. So along some direction, which is given by the similarity transformation S, what this is telling you is that along some direction, the two eigenvalues lambda 1 and lambda 2 are the ones that are going to decide basically all the properties of the system. And the lambda 1 and lambda 2 basically, if one of them is positive, then the positive one is going to dominate. It's the dominant eigenvector. If one of them is negative, that's the one that dies out, basically. And now you add in linearization of a nonlinear dynamical system near its fixed point, and you're just about beginning to do kind of the correct analysis for a nonlinear dynamical system. Now, what I want to just point out is that depending on what you have here, the two values of lambda 1 and lambda 2 produce basically a series of different kinds of solutions. So let's say both lambda 1 and lambda 2 are both positive numbers. Then what you basically have is basically just unstable nodes. Whereas if both of them are basically both of them are negative numbers, then you basically have stable nodes. If one of them is complex, then you basically can have things like spirals, and whether the spiral is stable or unstable depends on whether the other direction is dragging you down to zero or not, right? And you can have saddle points if you have basically one positive, one negative direction, and basically you can have these what are called stars and degenerate nodes along this kind of tau square minus 4 delta equals 0. So I won't dwell on this, but this is simply to represent two things I want you to take away from here, because maybe I have 10 more minutes before I stop. One thing that I want you to take away is basically that the trace and the determinant determine all the properties. And the second is basically that the eigenvalues basically are the ones that are driving this discussion, basically. Okay, so with that, the exact same thing is also true. An analogous thing is also true for open quantum systems. So that's the reason that I had that previous slide. So in open quantum systems, what you can do is you can write the eigenvalues of the Liouville superoperator. This Liouville superoperator L, you can write its eigenvalues down. And the eigenvalues lambda mu are actually complex in general because L is not Hermitian. And because L is not Hermitian, you have to now tell me what the properties of the eigenvalues are. The eigenvalues typically tend to be, the eigenvalues can only be, the real part of the eigenvalue can only be negative semi-definite, which means that they're not allowed to be positive semi-definite, the real part, because then the density matrix is not trace preserving, it blows up. And then basically, depending on where you are on the negative axis, on the real line and on the imaginary line, you get different solutions. So you get things that look like spirals. You get things that basically look like just decays. So nuclear decay problems are just sitting right here. They're just one example of this kind of physics. Steady states, of let's say the damped harmonic oscillators, so on and so forth, are all sitting over here, and their quantum analogs are all sitting over here. And then you have these new kind of very exciting things called oscillating coherences, which are sitting over here, just on the pure imaginary axis, where the expectation values can oscillate in time. And this has huge interest and applications in physics to things like boundary time crystals, to discrete time crystals, so on and so forth. So, and I'm happy to talk about them offline. Okay, so let me just quickly flash this slide. I will say no more about this, which is that at this point, you could simply stop and you could be a condensed matter theory student, and you could go off and spend a lot of real hard computational resources trying to solve this problem. And so, for instance, you could take the Lindblad operator or the Liouville superoperator, and you could basically apply Arnoldi and Langsauce type algorithms to it. So you could take the first n vectors that come up when you apply it on the initial state, and then you can use Gram-Schmidt orthogonalization, blah, 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 to basically make up the solution space to get the low-lying eigenspectrum. It's something that we do on a daily basis. The only thing you have to pay attention to when you go to Liouville space is that these things basically tend to be, they're not self-adjoint, and they also basically tend not to be invertible. And so you have to use some slightly additional, the slight additional complications in terms of what's called the Moore-Penrose pseudo-inverse that you have to pay attention to. Okay, so with that, let me just flash an application, and then I move on to the next part of the last part of my talk. An application that is in preparation. Sorry, I should have, I don't know why the thing is not appearing here. The reference is not appearing here. This is work that I did in collaboration with Bhaskar and Muralidharan, Muralidharan's group here in IIT Bombay, and there are several students involved, Adil, Anuran, and Parvinder, Bitan, so on and so forth. And so the reference is just missing here. So what we did was we basically worked on something called an entanglement switch. So it's a quantum dot. So here is the 3D diagram of cartoon of it, and here is a 2D schematic representation with all the chemical potentials and all kind of gory details in here. And the important thing that I want you to take away is that it's a thermal machine. So there are two temperatures, left temperature and right temperature. And basically it's driven basically by a voltage difference that you can apply to it. And what you can do is you can look at the combined quantum system composed of the fermionic degrees of freedom that are in the dot and the bosonic, the kind of the qubit degrees of freedom of two impurities which are just hanging outside. And basically, this combined quantum system is an open quantum system because it's talking to its environment. And you have to now write its level superoperator, you have to diagonalize it, so on and so forth. And so if you do all of that, then you get basically eigenspectra like this for different values of parameters in the problem. So this is some voltage, this is some other parameter, it doesn't matter, this is some other parameter. And so what you can see is you can see heat maps like this. So as you sweep the voltage, basically the entanglement switches on and then it switches off, and then it switches on again and it switches off again. And if you ask, why is this triangular shaped? Why is this square shaped? I'm interested in knowing this. I want to make a design of a quantum device. Then the theory that you have to go through is exactly the one that I've just explained. It's this level superoperator open quantum systems theory that you have to work out and then look at the eigenspectrum at every point in space, in this parameter space, and then you'll be able to find the solution to this. Okay. So, so with that, let me just say, there is something that I won't talk about, but I just want to flash because it's a super interesting topic and it's something that I've thought about a little bit as well, which is basically what about approximate solutions? So till now I've spoken about exactly solvable models and numerical integration. So I skipped approximate solution, and you can say, hey, I'm a little upset. What happened to approximate solution in the middle? It's actually a super large and very important part of the field. It's the most important part of I think real physical systems design. And the way it proceeds, I just want to flash one kind of overarching theory, which, you know, if you want to kind of at the end of this lecture go look up one thing, I recommend that this is the thing that you look up. And the thing is basically what's called the Feshbach projection operator formalism. Depending on where you look, it's called something slightly different. In the old school nuclear physics and atomic physics literature, this was just called the Feshbach projection operator formalism. And what it is the following, which is I have, let's say, low-lying energy. So let me just take the square well potential. So I have the low-lying energies of the bound states of a square well potential, and I'm interested in performing transitions between the square well, the different values, the different energies of a square well. But there is a whole continuum of energy levels on top, which is, you know, maybe outside of the potential barrier, right, above the potential barrier. The question that I can ask is, how do I only deal with the finite part of the spectrum and not deal with the infinite part of the spectrum? I don't care about it, right? You can realize that it's the same question. You know, it's saying I have a subspace I care about, and I have one that I don't care about. But it's roughly the same question as saying I have a system that I care about and an environment that I don't care about. And for exactly this reason, these are all related techniques. This is an analytical technique. And so what you can do is you can write the Schrodinger equation into a projected space, and then you can basically use some approximation techniques to basically write an equivalent Schrodinger equation for just the projected part that you care about, just the P that you care about. And the important thing here is that it involves basically a quantum system starting off in P, so starting here, going off to Q, going into the continuum, and from the continuum coming somewhere else into P. And so this P going to Q and then going back to P is basically a term that you wouldn't have properly calculated if you didn't do the approximate theory correctly. And this is an approximate theory because this is the first order correction to basically a matrix inverse, or matrix inverse of an unknown matrix with respect to a matrix whose inverse you know. And so let me just stop there, and let me just say this is called the Feshbach projection operator formalism in atomic and nuclear physics. It's called the Nakajima-Zwanzig method if you look somewhere else. It's called the adiabatic elimination method if you look in quantum optics textbooks. And it's called the Schrieffer-Wolff transformation, or it's related to the Schrieffer-Wolff transformation, which is quite common in modern condensed matter theory now. And so all of these derive themselves from basically tricks like this. And I just want to highlight that this is actually a very interesting direction to talk about. I'm just not talking about it because it's somewhat standard material nonetheless. Okay, so let me just take just a couple of more minutes and point out to you the very last thing that I want to talk about, which brings us into modern quantum computing as an era. I want to basically just highlight the problems here. I'll run out of time to talk about the solutions here. And this is basically the question of quantum simulation. Remember the central problem. The central problem with quantum systems is that there are Hilbert space grows exponentially, basically, right? And level superoperators are order n to the 4, right? N is the number. If n is the number of qubits, the Hilbert space underneath is 2 to the power of n. 2 to the power of 2 to the n dimensional. The density matrices are 2 to the n by 2 to the n. the Liouville superoperators are the square of that, right? So this thing grows very, very, very quickly into a very obscene number, basically. And so it's very difficult to simulate. It's very difficult to keep track of. And related to this point, not quite the same. And, I must be very, very careful in telling you that, I'm now drawing analogies with a very loose hand. Related to the same is basically this problem, which basically is the birth of quantum computing, is one of the ways to think about quantum computing, which is that there are problems that are easy for classical computers to solve. So this is what's called the class of problems is called P. And so, for instance, matrix multiplication. There are problems that are difficult for classical computers to solve. And for instance, this is the problem of factoring a number into a composite number into its primes. And then there are many problems in this class. So for instance, there are problems which are, graph isomorphism, traveling salesman, so on and so forth. And then there are problems that are even beyond this, which is basically what are called P-space problems, which are, several board games and so on and so forth with fixed resources. Anyway, the only thing that I want to mention is that is this little pink line here, which basically simply says the following in words. It says there are problems that are difficult for classical computers to solve, which means that they take an exponential amount of time for classical computers to solve, but that are polynomial for quantum computers, right? So this Q is quantum and P is polynomial. So this QP basically simply means I can do this in polynomial time. And so this is exactly where I want to park myself for the rest of the 5 minutes of this talk and ask questions about problems that are easy to solve on a quantum computer, or at least easy to simulate, and tell you that just because you can simulate it on a quantum computer doesn't mean the problem is over. Other problems emerge, and this is actually part of the rest of the challenges to kind of both theoretical and computational physics that I want to end with. Okay. So let me just give you a kind of very practical example of a kind of problem that people would want to look at. And this is maximizing or minimizing, optimizing the trace of the density matrix at a final time, rho f, right? We saw what a density matrix is. So I take a density matrix, I evolve it to some time. And now I want it to be as close as possible to a target density matrix, rho bar, that I give you, right? This is exactly, so this is a real number. And so this is exactly the same problem as basically a hill climbing problem that you've solved in kind of your calculus course. So you have a solution here, and that solution is the optimal solution that would actually maximize the function, and you need to hill climb your way up. How do you do this, right? And this is a question that you can ask. First, before I talk about how you do it, let me show you why you would want to do it. The reason that you would want to do it is because there are tremendous applications to things like quantum chemistry. So this problem of being able to solve the optimization with respect to some parameters on a quantum computer, so this is essentially a cartoon of quantum computer, on a quantum computer already has tremendous applications to quantum chemistry and so on and so forth. So this is one paper where you can begin to kind of look at that literature, for instance, right? And so this is the reason that you would want to solve these kinds of problems. So the problem boils down to an optimization question. So the question is basically, how do I perform optimization? And here, what I want to tell you is that there are kind of, there are classes of optimization. So if you have well-behaved functions, then you can optimize them very easily, which is you just compute gradients and you can use hill climbing, right? Typically, the problem that you run into is that higher dimensional functions get trapped in local maxima or minima. This is something that you have to pay attention to. And, notwithstanding all of this, variational principles is a great tool to set up the first order gradient algorithm, right? And so what do I mean by this? So suppose I want you to go back and look at your textbook on variational principles, just to remind yourself. So I write it down here. What I mean by this is that I write the variational principle for action. So I write the action as the integral over the Lagrangian. And then I do the first order variation of the action. And the first order variation varies the coordinate and varies the generalized velocity. And then what I then do is basically swap out degrees of freedom. And then I basically just I do integration by parts. And I get this minus d by dt of del L by del QK dot, right? And so this is the Euler-Lagrange equation. That's how I did it. What did I do? What was the mathematical toolbox in my hand? I wrote down the functional that I'm interested in, right? This will become the fidelity in a minute. And then I just did first order variation on it, right? What I want to also just highlight here is that variation is a completely general toolbox. It's not used right? And typically in our educational system, variational principle appears once when you're discussing Euler-Lagrange equation and disappears. It just goes away from the from the story and reappears when you're discussing Ritz variational principle, and again disappears from the story. And this is not the case. It's actually quite a general theory that can be used over and over again for all kinds of different problems. And just to kind of make that point, I'll skip over this because I'm running out of time. You can actually solve the. I'll just leave this here for anyone who wants to see it. You can solve the Newton-Raphson method as a variational principle, right? And so you can produce the Newton-Raphson out of thin air, out of variation principle. It's simply related to the fact that it's a calculus problem. Okay, so once again, we can apply this exact same technique to Ritz variation as well, and this is what we do when we basically write a variational ansatz for a wave function. What we're trying to do is we're trying to minimize the energy. That's all this slide says. I've just used a slightly general notation from this Reviso model physics that I again point you to. But let me just move on for the moment. All I want to say is basically the following, which is now I have an energy E that I want to minimize with respect to a trial wave function psi, and I want to minimize this. Minimization, maximization are the same problem, right? All I want to tell you is that there is a hierarchy of hardness of these problems. If you basically have an easy Hamiltonian, if you have a Hamiltonian whose ground state is fairly simple, which doesn't have large amount of entanglement, right? This is the point that I was basically saying that we'll come back to. Then you can just use the Fock basis, etc., and a lot of basically standard condensed matter kind of Drude model type physics at first pass is basically just this stuff. And so that's the easy stuff that people wrote down in the 50s and 60s, and we have them in our textbooks. The second, basically, which has intermediate entanglement, is the whole field of DMRG, which is a computational toolbox that people employ extensively, and it comes out of entanglement theory partly and has large applications to many body physics, and so I want to highlight that as well. And the third is basically quantum simulations as a whole toolbox that sits on top of all of this, if you are unable to get it done by DMRG and other techniques. And so I just want to highlight one or two things about this, and then I conclude. So why is this last solution even available to us? Why are we even discussing running things on quantum computers? Well, it's basically because there are industrial solutions now, industrial approaches towards building quantum computers, and so we have basically faith in industry and academic partnerships that basically between all of the kind of combined effort that's there now, that a quantum computer perhaps will make itself available in the near future. Already 60-ish qubits are available, for us to play around with, and so what you have is basically, we are in the so-called NISQ era, and so the NISQ era is simply characterized in the following way, which is basically that you have between 1 and 10,000 qubits in your hands, but none of them are error corrected, basically. So what that means is that you can't run the standard error correction things that you might discuss in, let's say, Shor's of Grover's. You can't do all of the standard quantum computing that you're interested in, but what can you do underneath? What can you do with less than 10,000 qubits? And the answer is quantum chemistry, which I already showed you. Approximate algorithms, quantum simulations, and so this is the universe that is in front of us, and it's a combination of quantum simulation, and computational techniques, and a lot of theoretical effort as well. Okay, and so what does this look like? What does one of these solutions look like? So this is what running simulations on a NISQ device looks like. What you have is basically an input state, and you have basically some state preparation, some pre-described state preparation. And then what you have is then you basically have a parametrized quantum circuit that you basically that you tune the parameters of the beam splitters and phase shifters if you want, and then you can make a basis change if you want, and then you can make measurements. And by using the measurements, you can do a feedback. So the whole story is basically about, I send in a quantum state, I parameterize it not on paper as psi of theta, but I parameterize it as a bunch of unitary transformations that are acting on my quantum state psi. And once I parameterize them as u of theta acting on a fixed input state psi, basically, then what I can then do is I can compute the energy expectation value, and then I have the Hamiltonian expectation value, and then I can optimize over the parameters. So, I compute the expectation value, and then I minimize over the parameters. So this is a quantum classical loop feedback method of doing this kind of stuff. And you can imagine that it has tremendous applications all over the place. So here, let me just pose to you 4 questions that are yet unanswered in the community to great satisfaction of everyone, which is basically, how do I extract the number psi theta, a psi theta, right? Just go back here. At this point, it's just basically just a wave function. And it has an exponential number of terms, right? This is the whole point of quantum computing. It has an exponential number of terms. What that means is that extracting each one of them is exponentially time consuming. And if you want to do a full tomography, it's exponentially time consuming. Now, how do you get around that? This is a question that is, I think, very relevant. The second is, how do I represent A on a computer, right? So if I'm interested in constructing the Hamiltonian expectation value, how do I do that? What does it mean to take an expectation value on a quantum computer? This makes no sense, right? Okay, I'm doing optimization, blah, 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 but right, I have to first be convinced that this expectation value is easy to extract, right? How do I represent my psi of theta? Is there a better way and a worse way to represent psi of theta? Which is to say, is there a better and worse way of representing the unitary operator u of theta, right? That's the parameterization. U of theta is the parameterization here. And then the very last thing is, how do I optimize this quantum state? And each of these has an answer. So how do I extract? There is this thing called the Hadamard test, but it's not favored. It has problems, and this discussion is something that is ongoing in the literature now. How do I represent on a quantum computer? There are linear combination of unitaries, something called polyword, something called block encoding. I urge you to look these things up. How do I represent psi of theta? There is hardware efficient ansatz, there is system aware ansatz, so on and so forth. Again, a very good point of research for anyone who's interested. And how do I optimize psi a psi? This has a huge number of problems, including something called the barren plateau problem, which is something that I just highlight just to kind of pique your interest in the topic. Okay, so let me just quickly conclude by saying that previous approaches, including this very nice PRL, previous approaches have tried to solve this kind of a problem, but they run into kind of this exact same problem that I talk about, which is this exponential number of numbers that you have to keep track of. And so the way they get rid of it is by making a sparsity assumption. So they demand that their underlying matrices are sparse. And so we recently overcame this. This is just an accepted PRL from a couple of days ago. And so this is another kind of point of interest that I can highlight to you, and I can talk about it offline. Okay, so let me just conclude, because I've run a little bit over my time. So let me just conclude by saying that from few body to many body problems, well, essentially what I've tried to kind of bring together today is that open quantum system evolution is both central to our understanding of the universe and is actually very difficult. As a problem, it's actually quite difficult to solve. There are vast number of applications to designing realistic quantum technology. So this is the reason why I kept weaving in and out of quantum chemistry for a little bit. I kept advertising, quantum computing here and there. There are all these different areas which are interconnected to this. Photosynthesis is connected to this problem in a very straightforward fashion. I've worked on it in the past. There are many interwoven theoretical and computational concepts that you can't just run away from. There is no way for you to kind of only stay on one side of this conversation, because just the conversation is complicated and you go where it takes you. And for large entanglement, open quantum systems are difficult to simulate. I put this in here just as a kind of additional kind of fine point, that open quantum systems are not always difficult to simulate. They're just that they're difficult to simulate if they have large entanglement in them. And these large entanglement open quantum systems, are a very, very interesting kind of subject onto themselves. But let me just conclude by saying that, this is intersected with this kind of hardware solutions that have come up by, Google and other kind of industrial and academic partners. The fact that we're making tens of qubits now, if not dozens of qubits now, these two have intersected into producing a new field onto themselves. And now instead of running solutions on a computer, on a classical computer, which is the essence of computational physics, and one bad way of describing computational physics, you can run solutions on a quantum computer, and that's a whole other ball game altogether, right? And so let me stop here and take any quick questions if you have. Thank you very much.
Thank you, Professor Sai. So I say that any of the some questions from the audience can be taken up quickly. Either you can unmute and speak or put it in the chat box, and I think Faraz would be able to put forth the queries. Questions from the audience, please.
If you raise your hand, we'll unmute you.
Okay, Professor Sai, I have the question. Of course, if you remember, I had asked the same question when you gave the lecture in the department. But again, the audience is here. I just want to ask, like, to what extent there's a lot of simulations and which you have very put up in a very simplistic way that we follow. But how far are we from the realization of physical computer?
So
Quantum
so a physical quantum computer. So there are any number of prototypes of basically a few number of qubits that are available. So let me split the question into two. One is, do we have an error-corrected quantum computer, which means a quantum computer that is fault tolerant, which can correct its own errors and run in a stable fashion? We don't. It's not clear how far away we are from it. I wouldn't venture a prediction per se. But do we have basically many bits, many quantum bits floating around? And the answer already is yes. So the kind of gold standard from like 2 years ago was basically 64 qubits, I think, which Google produced and IBM produced, and out of which basically maybe some 50 odd work. There's some ratio of them that work. And there was a Chinese experiment recently which has larger numbers, and then there was some controversy around it. So let me just say around 50-ish qubits people can produce and put in front of you, then you can try and use it basically, and it runs okay. The problem is that they're very noisy, which means that they're not particularly useful for the complicated tasks that we're trying to do. And now it's a kind of a hardware, it's an engineering problem, which is we just have to fine tune them, get the noises down, engineer wires, maybe make new FPGA protocols and this kinds of stuff, basically, to just really solve some persnickety hardware problems. And then the question of whether scaling, there is a fundamental physics limit to scaling will emerge. I don't think anyone thinks that there is a fundamental limit to kind of just scaling these things. I think the only problem is basically just readouts, basically, which are the complicated issues. Yeah. So there is a question by Sunil Ekawade. He's saying, would you talk about current quantum computers? That using current computers, what can we achieve, and what are the corrections to be made to current quantum computers? So that's the problem. I think this is essentially the point that I want to make, which is that for those who are interested, Sunil, if you're interested in this, I urge you to follow the same steps, which is for those who are interested in kind of really understanding, hey, what's the big difference between classical and quantum? You have to first understand what makes quantum difficult to simulate. Because if you don't understand what makes quantum difficult to simulate, then the separation between classical and quantum doesn't make any sense, right? So what makes quantum difficult to simulate is large amounts of entanglement. So if you have a quantum system that you want to simulate that's carrying a large amount of entanglement in its dynamics, then this becomes more and more complicated to simulate. And because this is more and more complicated to simulate, you actually need a real quantum computer there to simulate it. You can't just run it on a classical computer. That's what I mean when I say it's difficult to simulate. So if you look at real quantum computers now, real quantum computers are so noisy that our classical computers are better than them, right? But the moment a real quantum computer becomes very quiet, our classical computers will just become completely useless in comparison to that. So if you have a 60 qubit, let me just take 64, it's a nice number. If you have a 64 qubit quantum computer that's perfectly quiet, it would already outstrip basically all classical computation in some specific tasks that people have talked about in the literature. But because they're so noisy, basically, the noise basically makes them more and more near classical computers. And because they're so noisy, they're easily simulated by classical computers right now. And so there is this whole discussion, basically, I don't follow it too much, but I know enough to kind of just read around this issue. There is this whole discussion of what is called quantum supremacy. Can you prove that a quantum computer has really outbeaten every classical computation that exists in the world right now? And this quantum supremacy, basically, literature is very technical. So you can look it up, but what you'll run into is the following, which is somebody will make a claim that that they have a quantum computer and there is quantum supremacy. Google made that claim a couple of years ago. IBM, so on and so forth. And then you wait 3 months and somebody will respond and say, no, you're wrong. Here is a simulation that does it just fine. And it's basically because, all of this noise and so on and so forth make it so difficult to kind of really pin down this question of what is easy enough that a classical computer can do it and what is difficult enough that only a quantum computer can do it, right? So Sunil, I go back to your question. So you're saying, what can we achieve using a current quantum computer? The ones that exist right now, nothing, but I mean, it's essentially a work in progress, because you can't build a 100 qubit quantum computer before you build a 50 qubit quantum computer. So we have to just wait patiently till we cross the number from 50 to 100 to 150. And at some point, this becomes strong enough that basically classical computers won't be able to simulate this. Yeah. So there's one more question. I'll just quickly read it out. I wanted to ask, make a lead in creating a new dimension of quantum realm. What are now the limitations of? I don't understand the question, Lakshman Sharma. Do you want to just ask the question?
Hello?
Yeah, go ahead.
So good morning, sir.
Very good morning.
So,
I think once he unmutes, he mutes himself. He can't unmute himself back again.
I think essentially the question is on the limitation of technology. That is what.
I see.
Yeah.
yes, ma'am. Yes, ma'am.
I see. So the limitation on technology basically right now is, as I understand, I'm of course a theorist. As I understand it, there are several problems here. One is basically that different physical systems interact with basically their environment in different ways. And they interact with each other in different ways, both of which are required for quantum computing. So, for instance, superconducting devices basically interact with their environment in a particular way that produces, T1 and T2 certain decoherence. And what it means is that you have to work really hard to stabilize that decoherence and get rid of it, basically get rid of the noise. But they readily talk to each other. This is very easy to, On the other hand, light, for instance, linear optics basically doesn't interact too much with anything. It's perfectly fine, but it doesn't like to talk to each other as well. And so you have the first problem that you run into is even choosing the physical system. There are trapped ions, there is superconductors, there's semiconductor, quantum dot devices, there is light. What do you choose? And in light, there is not one. There is this version of qubits and those version of qubits and GKP and this and that and the other now. And which do you choose basically? And the question all boils down to how well do I interact with another copy of myself so that I can make control NOT gates and universal gates, and how weakly do I interact with the universe that I don't care about so that I'm not decohering information into it. This already puts you puts the technology limitation quite strongly, because you have to isolate the quantum system well enough, so on and so forth. The second problem that you run into is basically that once you put it, once you design the physical system, so on and so forth, you have to run wires in and you have to run wires out. So there are a lot of electronics issues as far as I've spoken to my friends who are doing experiments. There's a lot of issues like, I have only 4 wires I can take in, but I have to talk to the quantum system in 16 different ways. So how do I make 4 look like 16? And so this kind of basic electronics issues, which which basically are plaguing the field right now, because you have an exponential number of controls that you have to be able to execute basically for universal quantum computing. There are of course tons of solutions around this and so on and so forth, but we're just waiting on one stable solution to emerge basically. Yeah, so that's Lakshman Sharma. Professor Mishra, cut me off at any time, because I notice Professor Sudeshna has joined. So tell me if I'm so shall I? There are 2 more questions. Should I stop or should I?
Yeah, I think
I think we have to
basically what
stop
we
it.
can see is it's all coming in the same.
Okay. Yeah.
Right. So I would suggest that they can email either us or so that we
Sure.
can, because Prasai is always open to that. As he said last time, you can just
Yeah. Just ping me. Yeah. Yeah.
because of
We're
the
local.
time constraint that we have to move on.
Absolutely. I know I'm a little over time.
So I believe.
Thank you very much.
Yeah, we should. So it's a formal thanks to Professor Sai, and I would like to inform the students that we look forward, as this center's mandate, that we are looking forward for many kind of courses which students can take for additional credit or whatever, at all levels. And in fact, we even would prefer that undergrads would also be able to join. So with that, I thank Professor Sai once again.
Thank you
and
very much.
We'll be in touch for all this.
So
Thank you very much.
congratulations to the new center. Thank you very much.
Thank you, sir. So I think Professor Sudeshna Sinha has already joined. We'll have a break for 5 minutes and we'll start at 11:30. Hello, Sudeshna, you would like to check your slides or something? Hello. You need to unmute yourself. Yeah. You're the co-host, so you can.
It's just a second. It's not letting me unmute. Yes.
Unmuted.
Now I'm unmuted. Right? Yeah, it was not sort of letting me unmute for a bit. Let me see. So I have become co-host, is it?
Yes, you are a co-host. You can share your screen.
Let me just, yeah. It said host disabled participant. I'm still not co-host, I think. Let me just,
Is
yeah,
that-
I'm still not. It shows me as a participant still. So. Yeah, it's saying that it's disabled participant. It still actually hasn't made me co-host, Anuradha. I don't know how.
I'm trying again.
Yeah. Now it says host now. Let me try. Yeah. It says something. Let me try. Yes.
So welcome to you, and my colleague Radha Srinivasan is the moderator for this session.
Okay. Anuradha, you can see the slides right now?
Yes. You can
Okay, good.
So welcome, Professor Deshna.
I-
I am not able to get my camera on, but I believe you will recollect me having been in TIFR when I joined in
Right.
1987.
Yes.
So just a brief introduction to our audience. As Professor Sudeshna had completed a master's from IIT Kanpur and PhD from TIFR in 1990. She was a visiting scientist at ICTP Italy from 90 to 91, and then at BRC from 90 to 93. She joined the Indian Institute of Astrophysics from 94-96, and then the Institute of Mathematical Sciences, Chennai in 96 to 2011. She was also an associate member of ICTP from 95 to 2000. Presently, she is at ISER Mohali from 2010. She has been elected the Fellow of the World Academy of Sciences in 2018, Fellow of INSA and the Indian Academy of Sciences. She was awarded the J.C. Bose National Fellowship 2015 and the B.M. Birla Prize 1998. She works in the field of nonlinear physics. Today she is going to speak about the classical chaos. So over to you, Professor Sudeshna.
Yeah.
Welcoming you once again. Thank you.
Thank you. So I hope everyone can hear me. Right. Okay. So it's a great pleasure indeed to speak in this workshop celebrating the inauguration of your exciting new center. It does hold a lot of promise to, to foster and to mentor interesting research. I will, hope very interesting things will come out of it in the near future. Okay, so what I thought I would share with you is first, in very broad strokes, qualitative and perhaps a little imprecise, some concepts of chaos. And then I will go on to show how these concepts can feed into the broader concept of complex systems. Complex systems has now gained a lot of buzz because of the Nobel Prize of this year, which was given for groundbreaking, work on complexity. So after that, I'll just, whatever time is left, I will use it to illustrate some aspect of complex systems through one particular research thread of my own work. Okay, so that's the plan. Let's see how far we get. Okay. So one of the eternal quests of people in science and even people not in science is to foresee the future. Okay, namely to predict and to forecast. Okay, and though if you step back for 1 minute, you'll realize that this is possible, is made possible only because you rely on the regularity of the temporal phenomena. So if the temporal phenomena did not have a pattern, you cannot use what you know in hand to predict the future. It is actually a very basic thing which underlies it, which you don't even often say out aloud. Now, in this broad quest, of course, Newton's laws of motion, which you learn from high school onwards through BSc, through MSc, was one of the biggest revolutions of science, and in fact, maybe mathematics through calculus, over 300 years ago. Okay, so it's a centuries old framework. But what is amazing is it is still the workhorse of not just physics, it is a workhorse of engineering, it is even the workhorse of some contemporary biologies. So it spans disciplines, and it spans in physics itself, scales in time, in space. So even my colleagues who deal with nanomechanical oscillators in their labs, they use the framework. And of course, my astrophysics colleagues who in a very different space and time scale also use the framework successfully. Okay. So classical physics is what we are going to deal with in this particular this hour. Okay. And one of the beautiful physics things about it is that it is deterministic. Okay, so what would that mean? It means that if you know all the properties of the system, and so the system, you can mean a single particle, you can mean or have lots of particles in a box, or maybe to the entire weather patterns of our planet, or the evolution of the universe itself, whatever makes you, is your interest. So this system, if you have it in hand, and if you know the laws of physics, then of course you can perfectly predict the future. That is the essence of determinism, that you know how the system will evolve from state to state as time marches forward. And this is what allows a physicist to make predictions. So given a starting condition, initial conditions, a unique future can be predicted. This underlies a whole lot of, classical physics work. And to quote Pierre Laplace, who was a mathematician but wrote extensively on classical mechanics, he thought of the universe as a clockwork universe. Okay, so you plug in something and a unique outcome comes out from the other end of your box. So as I said, classical mechanics is actually, so when I say classical, it's just a polite word of saying very old. Okay, so it's an old field, which is still amazingly relevant. Okay, which is why it is taught across the board, not just for a physics course, but for an engineering course as well. Okay, which was, my undergraduate training. I did my classical mechanics with the engineers, and it was absolutely relevant to them. Many of them did not actually go on to study any quantum mechanics, but classical mechanics, they absolutely needed. So the other part, which is very nice about it, is that it gives a mathematically rigorous toolkit. So it is, in fact, a branch of mathematics called dynamical systems. It is taken to be a branch of mathematics. And so it forever is giving physicists theorems which we can work on, theorems which we can use to lay foundations for a lot of things that we know. Now, what is chaos? It is, you can think of it as a new kid in a very old block. So it is the new frontier of classical mechanics. It is a theory which has actually caused us to fundamentally reassess the way in which we view the classical physical world. Okay, so we are still in the classical world, it has told us something about the classical world which has made us rethink a lot of things which we thought we took for granted. So where is the surprise and why is it necessary? So the surprise was that a large range of simple natural processes exhibited enormously complex behavior. So complex that occasionally they appeared to be evolving under random forces rather than deterministic laws. So if you didn't know better that there was a classical deterministic system underlying it, you may have thought it was just jittering due to fluctuations. So this is the delicious contradiction. A completely deterministic system displayed exponential sensitivity to initial conditions, which rendered it essentially unpredictable. You did not think you would use the word determinism and unpredictability in the same sentence, but there you have it. So this necessitated a paradigm shift in understanding a classical system and led to the emergence of what people call a new science, the chaos theory. So a little bit of word on where the word chaos comes from. I find this interesting because chaos theory is so new that the word chaos was used in colloquial language in many, many different languages as it happened. So for instance, it is there in Greek cosmology, referring to something like an abyss, like a primeval, empty, sort of an empty, unordered state before things came into being, before order came into being. The Chinese apparently had a word for it, as Hao Bailin in his famous edited book had put. This I got off the internet. I hope it really does mean chaos. And more closer home, if you look at a Webster dictionary and look up chaos, it will tell you it's a confused, unorganized, disorderly state. In India, we love to use the word because it's there everywhere, from traffic to politics, so chaos is a well-loved colloquial word. But it appeared as a technical term in scientific literature for the first time in 1975. So that's how new it is. In a paper by Lee and York, it was actually a paper in a mathematics journal, Lee and York both being mathematicians primarily, and it was called Period 3 Implies Chaos. So that's where the word chaos appeared in the title as a technical term. So the thing is, I like to call this slide, Does God Play Dice? As a spin on Ian Stewart's book. So the key idea is this: the present determines the future, but the approximate present does not approximately determine the future. So irregular motion of a deterministic dynamical system that is so sensitive to initial conditions that it is impossible to predict in the long term with anything less than infinite and perfect representation of analog values. I put this in a little bit technically at the last bit, perfect representation of analog values, because a lot of you write programs, right? You write numerical, you do numerical computation. You go to your laptop, to your desktop, to your cluster, and you write a program. All of these programs depend on how you represent a real number. And that is to finite precision. And that itself has an enormous bearing on your numerical experiment, on your numerical simulation. That's what I will talk about. So the first hints that nature can be both deterministic and unpredictable actually goes back a very long time. Okay. It in fact is in the 1800s, I think, when the King of Sweden offered a prize. Okay, there's always a prize to motivate people, to anyone who could solve the so-called three-body problem. So two-body problem comes in textbooks. So say Earth and the sun, throw in a Jupiter, say, or throw in a moon. Okay, so the gravitational forces of a third body comes into play and it kicks in. So people thought, two you can deal with, so throw in the third body and let's see where it gets in. And the famous, renowned French mathematician Henri Poincaré won the prize, but without solving the problem, because it's a very hard problem, almost intractable. So instead of solving it, he wrote about the problem. Okay, so he described all the reasons. This is the way mathematicians do it, and he did it exactly like that. He described all the reasons why it couldn't be solved. And one of the important reasons he flagged was that small differences in the beginning of the system could lead to very, very big differences at the end. Okay, so this is what he had. Okay, so the second, I would say I skip 100 years almost, no, not 100 years, but little, maybe 60 years. And then I come to Edward Lorenz. Now computers or early computing machines have now come, okay? And he was working in MIT on the weather system. So he's also kind of like a mathematician, physicist, but working with weather models. So he was in the Department of, I think, Atmospheric Sciences. So he had a simple model, okay, of a weather, and he was simulating it. He stopped and restarted a simulation. And what he found was, serendipitously, that he got wildly different results. Okay, so this was a actual, manifestation of sensitivity to initial conditions without, it was a huge surprise. So what he saw that this tiny rounding of error, more, less than, so he managed to get, say, 1 million decimal places in, but this 1 part in 1 million would lead to a completely different behavior of the weather from his model. Okay, so in essence, he discovered chaos. This was in early 1960s. But what I find interesting is here is that it came because of the advent of technology, in particular because of the advent of a computing machine. That is when it really hit the physicists that there is something to classical mechanics which they are missing entirely. So normally when you start off a system with very small changes in the initial conditions, you get small changes in the output. That's what you expect, but not so for a chaotic system. So, the colloquial one goes that a tiny change, like a butterfly flapping its wings in South America, can lead to a very giant difference in the weather somewhere absolutely far away. Sometimes you dub it the butterfly effect, very colloquially, okay? And this, of course, means that a chaotic system, in effect, because of the finite precision, which is necessarily there in your numerical experiment, in your laboratory experiment, indeed in any model of nature. So this actually comes to bite you, because even if you're off by a tiniest bit, after some time, sometimes very short time, you will have no idea what the system is doing. This is, of course, terrible news for astrologers who are trying to sell you, predictions of an extremely large system, but, they are completely wrong. Now this concept has gone from Lee and York's mathematical paper to even popular imagination. And I thought I'll put these two very popular things. One is a popular bestseller. The other is a movie, which I went in to see just because the butterfly effect was there. And it had some rather imprecise notions of physics, but it just shows that even Hollywood is buying it. Okay, why should we bother about chaos? One line answer, it is widespread in nature. Now that you know it's there, wherever you look, you appear to find it. And I'll just put it in one very small illustrative way. You have a whole lot of you in your BSc, MSc textbooks studied, say, 2 problems very precisely. There are chapters related to it. One is the simple pendulum. One is a 2-body problem. And they allow precise analytical formulation, even if you don't want to approximate your pendulum with a simple harmonic oscillator, do all your elliptic integrals with a lot of hard work. Still, they allow the formulation of these problems and a solution as well, which is why they come in exams. You're supposed to know it. But take one leap of complexity, one small step, add one more bob to your simple pendulum and make it a double pendulum. Okay? 2 bodies. Or, as I said, from the Swedish king's problem, you add in a 3rd body to your 2-body problem, and all bets are off. These will actually lead to chaos. Here's a long exposure photograph of a pendulum, which is exhibiting chaotic motion. And you can see how complicated, even to the eye, it is. So now deterministic chaos, there's a 2-pronged attack to understand it. One is through what we call experimental math, or applied math to some people. These are numerical experiments, numerical simulations. this whole body of differential equations which you couldn't handle are now tractable through this. The other thing is laboratory experiments, starting from electrical circuits to chemical systems to fluids, which were, from the time of Liebschaber, and now even biological experiments. So it has given us insights which cuts across fields and has allowed us to look at things which first you had just given up, saying this classical system is what we call intractable. I cannot handle it. So now we have a way of handling it. So I'll put it in a slight mathematical framework now. The framework is of dynamical systems. It is, as I said, a branch of mathematics as well. It is the deterministic mathematical prescription for evolving the state of a system forward in time. If you use continuous time, you have differential equations, which is what you most likely have seen so far. You write a set of differential equations to describe evolution. These are often called flows in your phase space. The other way, which is very popular, also equivalent in some ways, is discrete time system. So you essentially look at it as an iteration of the state at some point, and the state at another point, and as you go on like that. So these are maps. So they have a real number. So n is an integer, which says integer time, like a stroboscope, and it tells you how the system evolves as you move forward in time. And your state x is a point, could be in a high dimensional phase space. And what you get out of these systems, either from your differential equation or from your map, is the orbit or the trajectory or the flow, which in principle will give you the entire dynamics of the system. Now the question is, I've said it's there everywhere. How large does a system have to be to exhibit chaos? The answer is rigorously. For n first order autonomous differential equations, n greater than equal to 3 is sufficient for chaos. So suppose you had 3, x, y, z were your variables. You wrote down first order equations, x dot equal to something, y dot equal to z dot equal to something. This sort of system is actually could be sufficient to show chaos. You don't need any more than that. If you go to maps, you can go even simpler. If a map is invertible, which just means that it has a unique inverse, then you need just 2. 2 is sufficient to show chaos. And if your map is non-invertible, that is to say your map does not have a unique inverse, then just a one-dimensional map can show chaos. So that's as simple as it gets. Just a one-dimensional map can show chaos. So here is a picture. This is a one-dimensional nonlinear discrete time system, which can show chaos. The first one came from population dynamics. So it's an inherently interdisciplinary science. Things come in from very different sources and have influenced nonlinear physics. So this one was motivated by a famous Nature paper by Robert May on population dynamics. That's why it's called logistic map. The second one actually is a more mathematical, more engineering sciences map, the shift map. And then there is a tent map, which I've put in here. And this is what you get by plugging in the iterates in time. So it's very simple. I start with some x, some number. I can do it even on a pocket calculator. And then put it into the function, get the next iterate. Put it back in the function, get the next iterate. That's all. But just look at the mess. This enormously complicated looking, seemingly random looking object has come from this completely deterministic, simple 1D map. That is the surprise. And the two basic operations which underlie it is a stretch and a fold. Okay, the fold keeps it in a finite phase space, because if two things are flying apart, they might become very different, their outcomes, but it's not that interesting because they're flying apart, so obviously. But if they are sort of folded back into the same space, they have to have to inhabit a small space, avoiding each other, doing complicated things, then your trajectory becomes absolutely amazing. Okay, here is a two-dimensional map. I thought I'd show you this one. So this comes from a map due to Arnold, and it's called a cat map, just to say that it's not just quantum mechanics that has cats. Classical mechanics also has very interesting cats. So this is a cat map. This has two variables, x and y. One is 2x plus y, one is x plus y, but there is a mod 1. Mod 1 folds it back. Okay, that's the fold operation. And here is this poor cat, and this is an illustrative thing of what happens in one iterate. Okay, just one iterate of the map. Such a simple map. Okay, you can put it in even in your head and do it. And I put it with a pixelated picture of a cute cat, which in one first part of the operation stretches it, and the mod 1 operation cuts it and puts it back into the box. And in one iterate, the cat is completely unrecognizable. Here is a classical system, simple 1D, which has done this enormously complicated thing in one step of your dynamical system. So the slightly imprecise first definition of chaos is it's sustained, disorderly looking, aperiodic long-term evolution. And the more precise definition is through a Lyapunov exponent, which you can define with respect to your trajectory, x of t, and how far a small deviation from a neighboring trajectory grows in time. So it picks up the exponential growth of nearby differences of nearby trajectories. Okay, so the precise definition actually picks up two limits. Both of these are very hard to estimate, even in a numerical program. So it's easy to write it down like as a formula, but hard to find actually values of it. One has to work quite hard for it. Okay, but essentially what it is doing is it's picking up the exponential divergence of nearby trajectories, which of course feeds in to the great sensitivity to small changes in initial conditions, which of course tells you that it is, though deterministic, effectively unpredictable. Okay. So now the basic questions that you might ask, okay, the fundamental challenging questions. Simple laws lead to such intricate structures. How? I've given you 2-3 examples already to tell you, the underlying thing. Now, such structures are ubiquitous in the physical world. People are looking around. Now, if you report an experiment in chaotic systems, people say, oh, of course, we knew it. It's so routine. Okay. Question is why? And the why is because it's so, even the simplest thing is giving it to you. And that is why it is so commonplace. And this thing, which sometimes people call complex, sometimes people might even call seemingly random, just to describe the disorderly trajectory, it seems to still have its own rules. They are embedded in it, in this mess. There are structures which is like a skeleton of this flesh of chaos. And that is what you have to try to unearth. Okay. And for an experimentalist, the difficult question is they see some irregular patterns. Is it from random noise or is it from a deterministic chaotic system? They would have to find ways to figure that out. And last thing is it is a truly interdisciplinary enterprise. Okay. People across the board on different disciplines do nonlinear science, and they are found in physics departments, in chemistry departments, in bio departments, of course, in the math department and engineering departments. Okay. One interesting now, the next thing about the new directions. These were low dimensional systems. I showed you a 1D map or a 2D map, or I said 3 coupled differential equations. Now, the next thing which people found was somehow if you put them together, put these things together, the whole was more than a sum of parts. So there was something which is called emergent complex phenomena, which could be very counterintuitive. And I'll just give you an illustration from my own work after this introduction, is that this thing is what makes the whole thing even more surprising. So just when people started feeling they were understanding low dimensional chaos, came these other attempts to put low dimensional systems together and see what emerges from coupled or linked local chaos. And what they found again was counterintuitive. Okay. And this sort of an attempt has now been recognized by the latest Nobel Prize, which indeed reads, was awarded for groundbreaking contributions to understanding complex systems. Okay, half of it, interestingly, went to Manabe and Hasselmann, who actually were doing physical modeling of Earth's climate. Okay, so as I said, the climate guys from Lorentz onwards has influenced the field. It was interesting to see how people in a completely different department sort of get the Nobel Prize in physics. And to Giorgio Parisi, who of course had a lot of influence on frameworks where disorder fluctuations feed into our understanding of physical systems. Now the word mathematical modeling is right here, okay? So I thought I'll show a few slides on it and then go for an illustrative example. What is, so now a little bit of changing gears. Mathematical modeling. Why do you do it and what is the thing there? So what is a model? It's a simplified mathematical representation of a system. Do remember, if you put everything in, you'll just say it's too much. Okay? So the way physicists work is that they try to get a simplified representation of the system, but the cleverness is what you put in the model. So you would like to put key features which play an essential role in understanding the phenomena. That is the idea. Okay. And so here is a little cartoon of how Picasso might have done it. Here is your cow, and there is this wonderful little schematic of the cow, which somehow actually captures the essence of the cow. That's the whole point, or bull, right, or whatever. Okay. So why do we do mathematical modeling? First, to explain data, which is now overwhelmingly large in amount from all fields. They're just coming to us to say, you people do complex systems research, find a way to understand it. Or as to quote Wigner, there is this unreasonable effectiveness of mathematics. So there's this huge amount of data, and you wouldn't have thought simple mathematical structures might be able to explain it, but it does. So that is the success of mathematical framework, which we want to take to raw data. So in order to do that, you will have to link together levels of hierarchies of explanation, okay? Because large aggregates cannot just be understood by simple extrapolation of a few constituents. Otherwise, if I know a low dimensional system, I know everything above it. That kind of reductionism doesn't work, okay? So you have to sort of integrate understanding level by level. So you want to get a few simple rules, essence, as I said, from which somehow the next level can be derived, or maybe more levels if you are more ambitious. And that is how the consequences arising from models are assessed, okay? And after you rationalize observed behavior from your model, you can use that model to predict the future outcomes. This is how people do models. You have data, you have a model to rationalize what you already have and use that to move forward, okay? So, and this is of course a very broad thing, right? I mean, after all, elementary entities of science, you build it, you put it at the foundational level, say, you know, from particle physics to atomic and molecular physics to many body physics to chemistry, maybe from physiology to psychology, maybe psychology to social sciences, you know, everyone builds on foundations. Now, what might seem is that, you know, that higher emergent level, you may think should be determined uniquely by the physics operating beneath it, in the level under it. But hierarchy does not imply this. So it does not say that the science X is just applied science Y. I cannot say physics is just applied math or chemistry is just applied physics. And the reason is that at each stage, you need new laws and new concepts. And that is the idea that you have to understand, is why complex system research is in itself a discipline. Okay? So it attempts more precise descriptions of such a system where there is a large number of interacting components. And of course, you assume that, and you know through experience, that it is not just a sum of parts. Okay? Okay? If it is not just a sum of parts, you will call it complex. Okay? And to quote Phil Anderson's, more is different. It's qualitatively different. It's not just 1, 2, 3 lots, but what you get at the next level is qualitatively different. Okay, so you can do many things. How could you make these models? You could, there's a whole spectrum. Some people might have simple cartoon-like models to complicated detailed models, depends on what you want. So you have simple conceptual on one side, detailed realistic on the other side. So, essentially you can say, consider spherical cow in vacuum, in zero gravity, vis-a-vis a particular brown cow with some number of spots in a specific position. So you have these two completely different ends of the spectrum. But researchers do both things and both are useful. That is the main thing. Okay. And what is the trade-off? The trade-off is between broad understanding, which you can get from a simple conceptual model, which will teach us how things work and make at least some qualitative and then quantitative predictions, to more specialized models, where you are almost trying to copy the real life, because you have to make very precise statements about something which is also narrow but precise. Okay, so you have to do both of these are useful. Okay, so increasing levels of abstraction gives you broad understanding, increasing levels of descriptions gives you quantitative predictions. And so basically you try to understand nature by the top-down approach. So you break down a system to gain insight into compositional subsystems. Probably a lot of high energy physics works that way. Each subsystem is refined in greater detail. Sometimes additional subsystems are necessary. Okay, and the entire specification is reduced to base elements. This is in the broad framework of analysis or decomposition or reductionism. And the one which we do in complex system is bottom up. You piece together system given to get a grander system made out of subsystems which are low dimensional. So you link together small systems to have an emergent system till the full top level system is formed. And this is what we call synthesis. So you have a seed model which you sort of understand to a good extent, and you grow in complexity and completeness. Okay. So in this business, you have to look for low dimensional dynamics then, and connections. Connections have two things: the form of the coupling and the topology of the links. So the ingredients to build a large interactive system is through low dimensional systems, local dynamics, and connections. These are the two ingredients. This is your recipe. I have two things. And the three things you must look for is space, time, and state variables. So state variables are the physical quantities of interest. These could be experimentally observed quantities, like, could be temperature, pressure, velocity, chemical concentration, maybe population density if you're looking at, population model, charge density, what have you. Okay, and time is time, and space, because you're looking at extended systems or collections of systems, space could be the different entities which make it up. So here is a hierarchy of models which you have. Partial differential equations where space is continuous, time is continuous, state variables are continuous. And those give the class of models which are partial differential equations. You can also have oscillator chains where space is discrete, which means you have different oscillators sitting in some chain or in a network maybe. So space is discrete, but they're given by differential equations. So time is continuous and the state variable is continuous. One more level in a very popular set of models, which I will show you in a minute now, are coupled map lattices. So maps, I've already told you, discrete time. So time is discrete. State variable, where you had X or whatever, is a real number. So is a real continuous variable. Space is also discrete. So I couple a set of maps, then space would be discrete, time would be discrete because they are maps, and the state variable is continuous. And at the bottom, I say bottom just in this hierarchy, but Wolfram will say it's the most fundamental model. I don't buy it totally, but it's a very powerful model still. It's a cellular automata where space is discrete, time is discrete, and state variables are also discrete, which means it has a finite state which describes the full system, and you just give update rules in discrete time to describe it. Extremely large number of extremely important models also fall in this class. Okay. And now I'll come a bit to my own work in the next, I don't know, 25 minutes or so, just to illustrate what you can, what you actually might expect from a certain model of a complex system. So this part would be to illustrate all the general stuff that I've said before. Okay. So let me now focus on a couple of outstanding questions in the business. Now I'll use the word complex networks, partly because I will explain why I say it. You can take it as complex systems as well. We will deal with linked local chaos. So local chaotic systems, which is the first 1/4 of my lecture, connected to the last few minutes of my lecture. So I link local chaos and see what happens. So what is the spatiotemporal behavior of a collection of elemental chaotic units with varying degrees of randomness in its connection? Okay, so as I said, 2 ingredients, local dynamics plus connections. The local dynamics is taken to be chaotic, therefore very complex, and the connections could have varying degrees of randomness or complexity. Okay, and so what emerges if you put these together, the interplay of the nodal dynamics and the changing links, what can happen? And what I'll show you quickly is that random links can suppress local chaos and induce global spatiotemporal order. So these were some old results of mine. And the only reason I thought I'll share it with you is to say that just when you think you're understanding the business and you say that here I have chaotic systems, I throw them all together and they are all talking to each other, what do you expect? More chaos, more disorder. However, what we found was actually random links of chaotic systems, which are extremely disorderly, acts as a suppressant of the chaos. So it manages, the connections manage to take the local chaos and produce global spatiotemporal order. Okay, so it gives a sort of mechanism which might be there in natural physical and biological systems, where you can get order out of chaos. And I would also try to show, if I have 2-3 minutes left, how it can also mitigate catastrophic blowups. So it does 2 very important jobs for us, coupling, by suppressing 2 things which may be runaway problems for our system. So now, specifically, this is in the class of models called coupled map lattices. Okay, consider a 1-dimensional ring of coupled nonlinear maps. Okay, each map was given by that prescription to take the state forward in discrete time. So here the sites, you can think of them as sites. If you think like a network, you can think of them as vertices or nodes, all equivalent ways of describing it. So discrete space, they are denoted by some integer 1 to n. Say 100 of them are put together. So 1 to 100. And you can think of this is the size of your lattice, if you think of it as a regular grid, or a network, if you're thinking more in terms of a general collection of things connected to each other in any which way. Okay. And what you're going to track is your state variable x, which is the physical variable of interest. Now, in this place, consider this prescription to move it forward. These are nearest neighbor interactions. This is the on-site map. This is the dynamics at a site. And these 2 are the connections to nearest neighbors. So site I talks to I plus 1 and I minus 1. Okay. And there is a coupling constant which tells you how strongly it connects to its neighbors. Okay. And let us take a fully chaotic logistic map at the site. So full chaos. Now this is what we call a bifurcation diagram. So on the x-axis is a coupling strength. On y-axis, I have put at each point in coupling strength a dot to say what is the state of the system in time. So, you know, say I follow 100 of these maps over 100 time steps, I put 100 times 100 dots in this thing. So it looks a mess. So clearly, you know, there is no order. This much you can tell, okay? And so, you know, there is a lot of complexity. This is nearest neighbor coupling. Now, I take the same ring and cut some of the nearest neighbor connections and rewire them to random places. So I replace fraction of nearest neighbor links and put randomness in there. So I've put spatial randomness in the connections now. So P equal to 0 means there's no probability of these random long range links. So then it's completely nearest neighbor, just sitting on a ring, which is how you would think is the simplest case. And P equal to 1 would means completely random coupling. So this is a picture. This is regular, say, all of them just talking to neighbors. This is called small world, where very small fraction of them get rewired. These are very, very good frameworks to understand phenomena in different fields. And this is completely random. They have, you know, some probability of connecting to any site in this system. And I could, of course, change the links in time, or I could keep them fixed. So let me change them in time. I have random links, and the random links are changing. And this is what you get. So even if you forget everything else that follows in this thing, I just want you to just look at this picture. This picture versus this picture. This was the system for regular nearest neighbor connections. And this is a system with the same chaotic maps, strongly chaotic, but under random connections. So that is why it's counterintuitive. Your random coupling actually gave you order, though the local dynamics in itself was completely chaotic. By connecting them together randomly, you got global order, stable global order. So if you took local chaos and connected them regularly, you got more of the same, more disorder. But if you throw in randomness in the connections, you get order. So that is why things are so not what you expect. Lots of scope for doing lots of neat little experiments and modeling, because you don't really know where, you know, what surprises are there around the corner. Okay. So basically then the spatiotemporal fixed point, where all the sites are sitting in the same value here, gains stability in a large range of coupling strength. Okay. And you can actually do a fairly rigorous calculation to understand this. And I will just show 2 slides on it. So the way I had done it was through a mean field version of the dynamics. It's a somewhat old work. So I essentially said that because the links are moving around so fast, each site on its own sees a blur of the connections. And in the blur, it picks up 1 minus P information from its nearest neighbors and and information from random sites weighted by P. So this is an averaged evolution equation for the system. Once I wrote this down, I could go through the machinery of linear stability analysis, which is just a way of finding out through the Jacobian of the system, where the stable fixed points are. And this is a calculation which could be done, which at the end of all the algebra gave a neat, easy expression, which happily matched what I got from numerical simulations. Okay, so regular nearest neighbor, which is P equal to 0, gives a null range for the order, which means it does not have any range in coupling where the spatiotemporal fixed point gains stability. All of it is you know, unstable. And P equal to 1, which is the most random connection, actually gives the largest range. That is the surprise. Okay, and here is a sort of which all of us do in the business. You do your simulations, you know, these points are from the simulation, The dotted line is from my analysis. Good, whatever, it's certainly consistent and very good agreement, in fact. And when P is small, you can see that it actually grows linearly, the range. So the more randomness you throw in, the better you do. Okay. And you can do it for different kinds of chaotic maps, because that's the second thing a modeler does. They take many different systems in order to prove the generality of the concept. Otherwise you get it for something, you don't get it for something, and then you don't know how much to push it. So here we did it for the tent map, which I already showed you, logistic map, which I showed you. Circle maps I haven't, but that's another class of maps which was checked. And indeed, my postdoc Shoma De later even checked it for a piecewise linear map, which showed what is called robust chaos. So it's a different class of maps, and she checked the generality of these results for that. Okay. The interesting thing is, if you did the same thing with frozen randomness, you did not get this. So there, your range of stability depended on how large your network was. So if your network was large, you'll get a very small range. Okay. So it fell with your system size, your range of order contracted. If your links were frozen, so they're random but frozen in time. Here, they were changing in time. They were randomly picking up links as you went along. So this is the summary. Regular lattice gave spatiotemporal chaos. No correlation in space, and the evolution of each site individually was chaotic. Full mess. Static rewiring, that is frozen random links, gave also spatiotemporal chaos for large enough systems. However, switched random links gave spatiotemporal fixed point. This is as different as two things can get. It's not like some subtle effect. It's like a huge effect, okay? And so there must be a change from static to dynamic links. How fast does a network have to rewire in order to induce spatiotemporal order? So a whole bunch of my students over bachelor student when this work. So they investigated various things. I'll show just two pictures from there. One is, here are two things. This is the same coupling strength on the x-axis, and this is the state of the system on the y. This gives you how often the rewiring time period. So here, every moment in time, it sees a new sort of set of connections. There you have a huge range where you have spatiotemporal fixed point, as we saw before. But as you rewire less frequently, that range shrinks. And how does it shrink? It shrinks in a way that there is an effective randomness, which is a product of the probability of finding random links times the rewiring frequency. So what you gain in spatial randomness, you might lose in temporal randomness. So it's a trade-off between, so if you have very few spatial random links, then you'd have to change those links fast enough to get order. However, if you have lots of spatial randomness, you need to change them much less often. Okay, so that is the whole thing. So it's both of them put together that does the job for you. So rapidly switched random links are the ones which work the best to enhance spatiotemporal regularity. Okay, now 3 or 4 things which are just pictures. Okay, so that was for maps, but in my table of hierarchy of models, I had other things as well. So I'll show pictures from 2 of them. One is going to be what would be coupled differential equations, what would be in the oscillator chain class of models. Discrete time, discrete space, continuous time, continuous state variable will be the first one. And I'll also show you a cellular automata, which is discrete everything, just to show that it's perfectly general. First one, was an example with my colleague who was mathematical biologist, who had this ring of coupled cells, which we thought we would look at. This was modeling a minimal biochemical pathway of a 3-step reaction sequence, and was used quite commonly to describe a lot of cellular systems. And so basically there are three objects, S1, S2, S3, and the reaction is mediated by an enzyme. And there are some feedback loops, and don't worry what it is. At the end, you have 3 coupled differential equations, okay? X dot, Y dot, Z dot. And they have some complicated functional form, but this is what is describing your system, the ring of cells. And the diffusion of the end product is the coupling. And here is a picture. On this hand side is P equal to 0. P equal to 0, remember, is a regular ring. So just a ring. Everyone has just nearest neighbor. No wrong connections, no cross connection, no shortcuts. Just neat, regular lattice. Here, this is space, 100 cells. This is time, 1,000 steps. Now, as you can see, there is some pattern, but it's not regular. I mean, there's some, there's some defects looking, and, it's very pretty, but it's there. Here, I have got the smallest number of cells which are cross-connected or randomly linked, okay? P is just 0.05, just 2 of them. And you see that it has straightened out the entire profile, which means at any point in time, if I took a snapshot, all the cells have the same state. They have got synchronized. So your random connection has synchronized your system. And this transition, as we found, was a P tending to 0 transition. That is to say, in the dilutest, even if I throw in 1 random link in the system, I managed to synchronize this whole bunch of nonlinear reaction pathways. Okay, and the last example here is a cellular automata model. Okay, this was a cellular automata model done by my student at that time, Vivek Kohar, as part of some one chapter of his thesis. So he was looking at infection spreading. Now, of course, everyone is doing infection spreading because of COVID. But this was 2013, and those days it was not like the fashionable thing to do or anything. But we did it because it's still it was a very interesting system, very interesting spatiotemporal system. And what he had found, now 8 years ago, was the following. So he was looking, people were doing all this work on infection spreading in networks, but no one was considering the fact that the links might change in the network. Right? Today, I might be in this locality, I might go to the mall, and, there some other guys might come in and out, or I might take a bus to another thing. These are all changing links in the model of your population. So no one was taking that into account. So Vivek did that. And this is one slide from his paper. And this said that the infected sites, so if you look at, this is the total number of infected sites. So if it's a big peak, if it's going up and down, with a lot high amplitude, it means that you have periodic outbreaks of the disease which are large. So, it's a bit like now in COVID, you've seen these things with big peaks. So you sort of, I don't have to explain it much to people. You're always tracking this. So the point here was that if the rewiring frequency was large, which means the network underlying your population was changing more rapidly, you actually ended up having a huge outbreak of disease, periodic outbreak of disease. So the epidemic was, of large proportion. Whereas if you actually had very lattice-like in the modeling language, or regular network in, in some other language, then, so P is 0 or close to 0, and the rewiring frequency is very, very, very slow. That is to say, once in a while you change connections, that's all. That gave this what is called an endemic thing, where there is, a little fluctuation. So everybody's sick. Well, on an average, there is some number, but it's not these huge outbreaks which are overwhelming your medical system. So this was what he had done in 2013, and it actually meant that quarantining, staying in your neighborhoods actually help because you're not changing your links. So that is the central thing. So the transition from low quasi-fixed state, analogous to endemic infection, to large self-sustained oscillation, which is analogous to periodic outbreak of disease, comes by when you change your links more frequently. So the disease cycles get more synchronized. It's the same, the underlying thing is your synchronization or control of your dynamical system, but this is applied to modeling a certain disease. Okay, so this is what he had shown. So I think I have just maybe 4 minutes left. Is that right, Radha? If someone could tell me 4 or 5 minutes. Okay, I don't hear. So I'll assume I have about 5 minutes left to the hour. And so I will skip these 2 slides and come to this one. Okay. So in the last 5 minutes, I'll indicate 2 more things. I'm sorry. Yeah. So I'll indicate 2 more things, and that is that in all of this, I was saying that your randomness was in your connections. But what if the randomness is in your constituent objects? So there are two ingredients always, local dynamics and connections. So I said local dynamics is chaos, connections are changing. Now the other thing that can happen is that your connections are what they are, but your dynamical systems at the nodes are different. So there's heterogeneity in the nodes. Now what we had shown was that if that is the case also, so it's a different kind of randomness, it's in the nodal dynamics. There too, you could suppress chaos, for instance, in a whole ensemble of chaotic systems by coupling to just one dissimilar system. So that's very powerful. It's like a pacemaker. So you have a whole bunch of chaotic systems connected to one different object outside. And that is enough to grab all of these and suppress the chaos. So the other way of doing it, and this was work done much more recently with people who some of you recognize are from IIT Bombay. So I thought I'll put a little bit of Bombay work in here as well. So Sudhanshu was my PhD student, now a postdoc in that group. And they also did experiments. And so what we went on to also show was this kind of asymmetry-induced suppression could also be done in other types of connection systems. So like a ring of objects. So in the ring, you replace one guy by something else. Okay. All chaotic. It's not like I've suppressed it by putting one regular object. They're all chaotic. They are just dissimilar chaotic objects. Okay. And the last thing which we showed just a few months ago was to say that you don't even need dynamical dissimilarity. If the same sort of system has different time scales and the time scales are unmatched, okay, or mismatched or ill-matched, that also can suppress chaos or suppress chaotic oscillations. Okay. So basically heterogeneity or randomness, either in connections or in the nodal thing, induces order. Okay. So here is from the experiment, one small thing. So here they have put the coupling on and off just to demonstrate. So when coupling is on, so when it is off, the two systems, there are many systems. I've shown just 2 of them, one in red, one in green. The others are doing stuff like that. And they are doing something very messy, and they are not fixed points. But the moment you switch it on, there are 2 very different dynamics. One looks like this, one looks like that. But when they talk to each other, they both bring each other down to a fixed point. So you can keep switching it on and off to see, just for the, for fun, to see how it keeps inducing this fixed point. Okay. And the last 2 minutes, I will indicate one last thing which random links can do for you. And this is also something which bothers physicists. And that is some differential equations, some systems show unbounded growth in finite time. These are what you call blow-ups. They're really bad, and certainly bad for an engineer, but also bad in terms of theoretical understanding, because no one likes infinities. It's not something you want to deal with. Okay, so, but there are lots of differential equations, and for the ones which model classical systems, they are very much there as well, that you find cases where these unbounded growth or blow-ups happen. And in fact, my student at that time, Anshul, was very sad because I asked him to go and do some numerical simulations, and he came back and said that everything is blowing up, everything is showing infinities, and something is wrong, but nothing was wrong. The point was the system was blowing up. And he had a ring. So he said, see, everything is so neat and regular, and this is happening. Then I said, okay, let's switch it around. Let's randomize the connections. Does that help or does that not help? Okay. Since we have some idea that counterintuitively randomness might help. So here it was, he had this picture, and that's what he found. That the blow up was prevented, and faster rewiring led to even synchronization and blow up prevention. Slower rewiring led to certainly mitigation of the blow up, though not synchronization. But everything was bounded nicely once the connections were switched around and made random. Okay, so randomness to the rescue again. And here is a picture of a model of a neuron, which is a very popular model called a Fitzhugh-Nagumo model. And in this one, these coupled neurons have, without these rewired connections, have a runaway growth. So there's this red line, which is, if I let it go, will hit the roof in no time. So it's unbounded growth, hits infinity in no time, this red one here. Whereas with rewiring, they're all nicely bounded. So here it is. Without rewiring, it does one chakkar and then runs off. And with rewiring, they are bounded. So explosive growth is prevented. Okay, and I don't want to show this, but the link probability as you change gives you this yellow region. In this case is a good region where things are bounded, and this thing happens the more often you rewire, and the more probability of rewiring to random connections. Okay, I'll skip this. So this is my last slide, and I will take questions after this. So what have I tried to do? So I had tried to start with two general introductions. One was to chaos, which happened in low dimensional things. Then I went on to complex systems, where you linked together local chaos and built models of a more complicated object, and tried to look for, what were you looking for emergent phenomena. So phenomena which you wouldn't have guessed at the lower level. And so the thing that you are playing around with is the nodal dynamics and the connectivity. So it's the interplay of these two which is giving you all this phenomena at the next level of hierarchy. And what I showed you through a few examples from my own work at the end was counterintuitive phenomena, which you wouldn't have guessed from the lower hierarchical level. That's why I said, that is why it's emergent, because it is a collective phenomena which came about, which you would not have thought of if you just made an extrapolation from local to global. So what we showed was that random links can suppress local chaos and give global spatiotemporal order. So two things, two disorders, disorder in connections plus disorder in nodal dynamics somehow kill each other to give order. And the last thing, which I just brushed through, but just thought I'd mention, is that these connections can also mitigate catastrophic blowups or explosive unbounded growth. And this is important is in certain contexts, especially if you're making engineering systems. Okay, so that's what I have, and I'll stop here. Yeah.
Thank you, Sudeshna, for that wonderful talk. So now I think this is open for questions from the audience. So please unmute and pose your questions after raising your hand.
Radha, they will raise their hands and then you have to unmute them.
Okay, yeah. Fine.
Actually, I had also got muted in the middle, so I could not answer when Sudeshna
Yeah,
asked.
so Lakshman Sharma has a question again. Yeah. Can read it. Ask, he's asking
In the
that
chat, is it? Oh, there's something in, there's a chat thing. Sorry.
chat
I didn't
question.
see.
Yeah.
Lakshman, I
wanted
have,
to ask,
I'm unmuting you. I
could
think
they
I'm on this now.
have a time? Oh, okay. No. Okay.
I'm not. Yeah, I'm the host, so I can unmute you.
Right. I can also read it. So, yeah. So trust someone to ask a question, which not just I can't answer, but no one in our field can answer, because of course it is not a question posed within our framework. So the question, the answer to that is simple. If you have a dynamical system, this is a general answer, not a specific answer to a thing. If you have a dynamical system which is used as a model of some phenomena, and if that system shows chaos, then there's chaos from time t equal to 0, right? Because that is your system's dynamic system. Now, so a lot of descriptions which of certain systems are not so well defined as a system of coupled differential equations. If they are, the question is completely well posed. Does that system set of equations support chaos? Does that system, what are the parameter regimes where it happens, where it doesn't happen? These are well posed questions which people can study and go ahead. Now here, I don't know, I do know people in modeling have addressed in the context of their models, whether it's there or not. But I don't think there is a single umbrella answer to that question. But one thing I found interesting is that when you asked this question, it was like the first idea of chaos which the Greeks had, God knows, centuries ago, where chaos was supposed to be pre-order. But actually, that is not the way to look at it. In the mathematical framework, you have to look at it as a dynamical system, which could be differential equations or maps. And then you have to see whether that set of differential equations or maps have positive Lyapunov exponent, which would be technically a chaotic system. So someone has asked, to get order in chaotic systems, we need to add a random factor. Oh, no, I'm sorry. Okay, I must answer this question. So that is what I hope I thought I said in the first few slides. It is intrinsic to a perfectly deterministic system. That's why it's called deterministic chaos. Because the system that you have, it's a completely neat formula which has no random factors. There is no noise. There is no fluctuation. Okay, so I'll go and show it one more time, all the way up to the first few slides. Okay, so right here, no. So say this one. Okay, this messy thing here. Okay, I have not added any noise. I have not added any fluctuations. I have just put, I think I put I put this one, I think, in this one. It doesn't matter. All of them look the same. So I have just implemented this iterated equation. You see how simple it is. X is some real number. I have plugged it into this formula. R is some number, say 4. So I'm just saying 4 times x, 1 minus x, and I get the new one. Take that x, make 4 times x, 1 minus x, get the next number. And that gives me an orbit. And that's what I'm plotting here, and see how complicated it is. So no randomness from outside, absolutely no randomness. So it's intrinsic. So it is. So that's why people were so surprised, because things did look random looking. Like if I look at this and I say, you go to your random number generator and just put dots wherever you get, you'll get something like this. So, but the interesting thing is something so simple and so clean and without anything also gave something so random looking. So that is the surprise, that it's deterministic, but complex and random looking. Yeah, I don't know if I answered the question. Okay, so there are various ways you identify chaos sensitivity. Do we have necessary? So you have also asked, do we have necessary and sufficient condition? System is chaotic. Necessary and sufficient condition is that it should have positive Lyapunov exponent. That is the I would may have had it somewhere. I had a slide on it somewhere. Okay, so the necessary and sufficient condition is positive Lyapunov exponent, which is just a way of I seem to have lost my slide. I don't know where it was. Now you've got a quick run through everything. Okay, I can't find it. But I remember showing it. So basically, it gives you the exponential divergence of nearby trajectories, and that is a quantitative measure. Okay, so that's a quantitative measure. So if it is positive, it shows that it is e to the power some positive number times t. So which means that even if I had an infinitesimally small difference from one trajectory, the other one is going to exponentially diverge from it. So that is actually the necessary and sufficient condition for here. But what you would need from the system, though, is non-linearity, or certainly not linearity. So for instance, the simplest one I showed you here, 1 minute, this one. This is non-linear because it has quadratic non-linearity, x square non-linear. These are even simpler. So they look linear. This is 2x, but they are piecewise linear. So one is tent map because it's like two pieces like that in a box. The other is 2x mod 1, which is two straight lines like that. So they're piecewise linear. So the only thing which will not do it for you is linearity, because that won't keep it bounded in the box. So, but you do need non-linearity or at least piecewise linear. So that would be necessary and sufficient for a system to be able to have the capacity to show chaos. Okay. Yeah. I don't know. Is there?
Yeah, any more questions?
Just one second.
You can raise your hand. You can use the raise hand option and I can unmute you. 2 minutes.
I saw another question in the chat box. I can read it out. Oh, is it the same one? Maybe that was the same
Oh,
one.
that's the same one.
Yeah, the same one. Yeah,
Yeah,
that looked like the same one. Yeah.
Yeah, one thing, Sudeshna, I would like to say here is now that we are going for this, we used to have a lot of students who are doing this electronics, and electronics is always perceived as lab exercise. But now I think they very well will understand and appreciate, when we talk about all this noise and this is linear or non-linear systems. In fact, some of the students are from this who are asking you the question. So now my idea is that now with this center conceived, right away we have a problem or a small course, because I remember when we were at this TIFA graduate school, Roy gave this course and we were asked to plot it on that mainframe and go to that through wax and all that. But now with all this
in 30 seconds you can do it. Yeah,
we should be able to. So there should be some kind. I think teachers need to understand like what are the problems that we could give for the undergrads and then the PGs and so on, which can be taken by all the students. So that is the my request. Maybe I should.
This is in fact a very, very important point, because I mean, like a Chua circuit is just exactly that, a three-dimensional object, which is this minimal in this minimal category, and you can set up a Chua circuit with pretty simply in the lab, and then you see the chaotic orbit on the oscilloscope, so it feels very nice. And the little bit of noise which will come, because your table might shake and your parametry, the parameters will be a little fuzzy, but that won't matter really, because the attractor is quite robust and you will see it very easily in the lab. And that's fun because you can simulate it also
Yeah.
Yeah, so that would be nice if they do those things, and they can actually couple two of them together also,
That's it, yeah.
resistively. So you'll have at least a couple system.
Yeah, because
Can be
academy experiments have, Professor Srinivasan's kit
Yeah, he
has
had a
got
nice
that
set. He had a
experiment.
very nice set. Yes.
And I'm also announcing that, you can even consider it as a invitation that in December we are having a refresher course for the teachers. So what I thought is, we begin with giving a session for the teachers where, all even electronics and all these circuits, as you said, rightly said, we demonstrate and then we should be able to see the phenomenon in this light.
Right.
So that is the thing which I'm perceiving. And we hope a lot of things can be done with this center, and our students will be equipped with to learn all this. So that is my, I think, question, comment, whatever.
Yeah, that would be very nice, because in some sense, each system is very simple. So, but the consequences of that simplicity is quite a lot.
That's
That is the fun part. Even in the modeling, you can tweak these things and, get a different model and see what the consequences are. And some of it are small research problems, because, as I said, some of those people who did it were actually very young.
Yeah, that's it.
Some of the problems.
Yeah. So
that was a wonderful talk. Very nicely, you started with the very basics in a simple way and came up called your path-breaking work. I was just wondering, there was something about a biological system, a differential equation on slide 64 or something.
Oh God,
I was
yes.
just wondering, where do they get these equations from?
Right. Actually, this set of equations which were there was from, I should have a more efficient way of going. This one, right?
465, yeah.
Yes. So this was actually, these are just chemical reaction equations, because if you from when we used to do chemistry, I mean, well, you all may have done less of it, I've done a bit more of it. So there, when you did chemical dynamics, they are all differential equations. At the end of the day, if you look at it as math, it's just differential equations. So all you really need to do is to see which species influences the next level of your so essentially it's like a pathway of reactions, and each concentration, so these are all concentrations, so they just influence the rate of production of the next level. So this was a three chemical where Z was the end point of that sequence of, so basically there's here is a little bit of detail. Substrate S is converted to another one that they call it substrate, and each of these are mediated by some enzymes. So the feedback loop is what gives you non-linearity. It'll give you some X times Y type of connections. Otherwise, it's just a linear thing. So here the feedback loop means that the concentration at one level goes back and influences the one on top, and the top, so there's some coupled thing. And so one here is a negative feedback loop. So this is actually a very generic biochemical pathway, which I had got from my mathematical biologist friends, which is quite generic to cell function, what they had said. So of course, in real life, there'll be 100 species and there'll be a very complicated thing, but this is a minimal, so that's why I think I use the word minimal biochemical pathway of a 3-step reaction sequence. 3-step will give you X, Y, Z, and each of these sequences gives you a differential equation.
So all the objectives of the center actually came out in this one talk.
Because there was some disease modeling also, I thought I'll put, since you liked it once. So, yeah. Okay.
Yeah.
So done. Okay, bye. Okay, so I hope we can stay in touch, and wish you the very best for your really interesting center. And yeah, so should we end here now?
Let's clap for Sarasina.
okay.
Okay,
Yeah.
okay.
Thank you for the wonderful talk, Professor Sudeshna. And it's, as Professor Mishra has said, it's a right thing. I mean, it brings about the interdisciplinary aspect. And you already have our students, in waiting now that as I already saw the electronic students participating. And
Yeah.
there are actually also this neural networks which are mapped like circuits. And I
Yeah,
think
yeah,
we have a lot of things which we can
Oh, yes,
look
yes.
forward to address.
Yeah, there are very nice neuronal models. I mean, starting from the one which was Nobel Prize winning by Hodgkin Huxley, which is a very simple. There are lots of them. It's great fun. Yeah, that part is very nice. Yeah, one can do a lot of things. Yeah.
So on
Okay.
behalf of all the students and faculty and the department, I extend my warm thanks to Professor Sudeshna, and we
Thank
can
you,
look
ma'am.
forward to a lot of
Yes.
interactions in the coming days.
Yeah, sure.
Thank you.
Okay, bye. I'll log out now. Bye.
So students will meet again at 2 o'clock. Please be punctual because people will start coming, and by that time the talk is half over. So we'll start sharp at 2 o'clock for the next talk. Thank you.